Hello, and welcome to the Sleepy Astronomer. Tonight, we're drifting back through the ages to explore humanity's longest journey, not across oceans or continents, but across the vast darkness above our heads, following the gentle persistence of human curiosity as it reached from ancient campfires toward distant stars. From the first wondering glance upward by our earliest ancestors to the breathtaking images captured by the James Webb Space Telescope, we'll discover how the simple act of looking up has shaped our understanding of everything from time itself to our place in an infinite cosmos. We'll explore the patient observations of ancient stargazers, the revolutionary insights of Renaissance astronomers, and the technological marvels that now allow us to peer back toward the very beginning of time itself. If you're new to these contemplative explorations of the cosmos, welcome to our quiet corner of the universe. And if you've wandered here before from previous astronomical meditations, it's lovely to have you return to this peaceful place among the stars. Where might you be listening from as we begin tonight's journey? Perhaps you're nestled somewhere cozy as twilight deepens around you, or finding a moment of calm as the world outside grows quiet. Maybe you're in a place where dawn is still hours away, or where the first hints of morning are just beginning to touch the horizon. I do so love reading your comments about where you're joining me from. There's something deeply moving about discovering all the different corners of our world where fellow stargazers are pausing to wonder about the cosmos. I always find it wonderfully comforting to imagine all of us scattered across our turning planet, each looking up at the same celestial dome that has captivated human imagination since the very beginning of consciousness. If tonight's gentle exploration of humanity's quest to understand the cosmos helps you unwind, or if you find yourself marveling at the dedication of those who spent lifetimes mapping the movements of planets and stars, feel free to give the video a like. And if you'd like to help other space enthusiasts discover these peaceful astronomical journeys, a subscription really does help the channel reach fellow dreamers looking for calming content to drift off to. It means the universe to me, and it helps build this wonderful community of curious minds and starlight admirers. I'm always curious about which chapters of cosmic history you'd like to explore together, so please leave your suggestions in the comments. Perhaps you're wondering about black holes, dreaming of distant galaxies, or curious about the search for life among the stars. Your ideas help guide where our gentle spacecraft will sail next through the infinite ocean of discovery. Tonight we'll begin in the darkness before written history, with our earliest ancestors gazing up at a sky unmarked by city lights, and then gently follow the thread of human curiosity as it weaves through ancient civilizations, medieval scholars, Renaissance revolutionaries, and modern space explorers. We'll discover not just what they learned about the stars, but why they looked up in the first place, what it is about the night sky that has called to human hearts across every culture and every age. We'll explore how the simple desire to understand the movements of sun, moon, and stars grew into navigation, agriculture, and timekeeping, then blossomed into mathematics, physics, and philosophy. We'll meet the patient observers who spent decades tracking planetary motions, the bold thinkers who dared to imagine Earth was not the center of everything, and the ingenious inventors who built instruments to see farther than human eyes had ever seen before. We'll discover how each generation of stargazers built upon the discoveries of those who came before, creating an unbroken chain of curiosity that stretches from ancient Babylon to the launch pads of modern space telescopes. We'll see how the same sense of wonder that made a shepherd pause to watch the stars has grown into our current ability to detect planets orbiting distant suns and peer back toward the very moment when the universe began. So find your most comfortable position, whether you're curled up in bed, settled on the sofa, or perhaps lying back in a chair where you can see the same stars that have guided human curiosity for millennia. Take a deep breath, and let's begin our gentle drift through time to explore humanity's greatest adventure, the slow, patient, wonderful journey of learning to read the story written in light across the darkness of space. The story begins, as all the best stories do, with someone looking up and wondering what they saw there among the stars. Picture this. It's perhaps 50,000 years ago, somewhere in what we now call Africa. A small group of our earliest ancestors has made camp for the night, their fire crackling softly against the enormous darkness that surrounds them. As the flames settle into glowing embers, someone, perhaps a young mother nursing her child or an elder whose hunting days are behind him, tilts their head back and looks up. What they see takes their breath away. Above them stretches a dome of darkness so complete that it makes our modern night sky seem pale by comparison. There are no city lights to wash out the fainter stars, no aircraft blinking their way across the heavens, no satellites tracing their silent paths around the Earth, just pure, infinite darkness punctuated by thousands upon thousands of points of light, so many that they seem to flow together like a river of luminescence across the sky. This is the Milky Way as our ancestors knew it, not as a faint smudge barely visible from suburban backyards, but as a brilliant stream of starlight so bright it casts shadows on the ground below. The stars themselves appear larger, more colourful, more alive than anything we can see today through the veil of atmospheric pollution and artificial light that shrouds our modern world. And in that moment of looking up, something profound happens, something that separates us from every other species on Earth. Our ancestor doesn't just see the stars, they wonder about them. What are those lights? Why do they move across the sky in such orderly patterns? Why do some seem brighter than others? Why do new patterns appear with the changing seasons, while others remain constant? These questions, whispered around countless campfires across countless generations, mark the beginning of humanity's greatest intellectual adventure. We don't know the name of that first person who looked up and wondered. We never will. But we know they existed, because the capacity for wonder, for curiosity about the natural world, seems to be woven into the very fabric of human consciousness. Archaeological evidence suggests that even our earliest ancestors were tracking celestial patterns, noting the relationships between the movements of sun, moon, and stars, and the changing seasons that governed their survival. Cave paintings from over 30,000 years ago show star patterns and lunar phases. Bone fragments from the same period bear scratches that appear to track lunar cycles with remarkable precision. These aren't random marks, they show careful, patient observation carried out over months and years. Someone was watching the sky with the dedication of a scientist, even though the word science wouldn't be invented for tens of thousands of years. But why? Why did our ancestors devote precious time and mental energy to watching the sky when their days were filled with the immediate challenges of finding food, avoiding predators, and surviving in a world that offered few comforts and many dangers? The answer lies in something beautiful about human nature. We are pattern-seeking creatures. Our brains are constantly looking for connections, relationships, and recurring themes in the world around us. It's a survival trait that served our ancestors well, the ability to recognize that certain cloud formations preceded storms, that the behavior of animals might signal the approach of dangerous weather, that the position of the sun could guide them back to shelter before darkness fell. But this pattern-seeking tendency, once it evolved, didn't limit itself to immediate survival needs. It expanded to encompass the entire observable world, including the vast, mysterious realm above our heads. And there, in the night sky, our ancestors discovered the most reliable patterns of all. The sun rises in the east and sets in the west day after day with comforting predictability. The moon goes through its phases in a cycle that repeats every 29 or 30 days. Certain stars appear in the same positions relative to each other, night after night, year after year. Other stars seem to wander among the fixed patterns, but even their wandering follows rules that patient observation can discern. These celestial rhythms offered something precious to our ancestors, the first reliable calendar. Long before written language, before agriculture, before permanent settlements, humans were using the sky to track the passage of time on scales longer than a single day. The phases of the moon provided a natural unit for measuring periods of weeks and months. The changing positions of constellations mark the progression of seasons. This wasn't just intellectual curiosity. It was practical knowledge that could mean the difference between life and death. Knowing when winter was approaching meant knowing when to begin storing food and seeking shelter. Understanding the relationship between star patterns and seasonal changes meant being able to predict when certain animals would migrate, when certain plants would bear fruit, when rivers might flood or streams might run dry. But even as our ancestors developed this practical relationship with the sky, something else was happening. The night sky was teaching them that the world was far larger and more mysterious than they had imagined. Those thousands of stars, that brilliant river of the Milky Way, those wandering planets, they hinted at realms beyond the immediate world of forests and plains, water and fire. And this realization sparked something extraordinary. The first questions about our place in the universe. Who were we, these small beings gathered around tiny fires, in relationship to those vast lights above? Were the stars distant suns or something else entirely? Did they influence events on Earth? Or were they simply beautiful decorations scattered across the sky? Was there intelligence behind their orderly movements? Or were they following natural laws that might someday be understood? These questions couldn't be answered by direct experience. You couldn't hunt a star or taste it or touch it. You could only watch and think and wonder, and in doing so, our ancestors were taking the first tentative steps toward a way of understanding the world that would eventually become science. Different groups of early humans, scattered across different continents, developed different answers to these fundamental questions. But remarkably, certain themes appeared again and again in cultures that had no contact with each other. The idea that the sky was a dome or sphere surrounding the earth. The notion that the movements of celestial bodies were connected to earthly events. The belief that careful observation of the heavens could reveal truths about the nature of existence itself. Some cultures saw the stars as the campfires of ancestors who had gone to live in the sky. Others imagined them as holes in the dome of heaven, allowing divine light to shine through. Still others thought of them as distant islands in a cosmic ocean, or as the eyes of gods watching over the world below. The Milky Way, in particular, captured imaginations across cultures. The ancient Greeks saw it as spilled milk from the breast of the goddess Hera. Norse mythology described it as the path taken by souls travelling to Valhalla. Aboriginal Australians viewed it as a river where ancestral spirits lived. Many Native American tribes saw it as a path of spirits, while others described it as a seam in the sky where the world above showed through. Despite these different explanations, the underlying human response was remarkably consistent. The night sky inspired awe, wonder, and a deep desire to understand humanity's place in the larger cosmos. This response appears to be universal among human cultures, suggesting that the capacity for astronomical wonder is hardwired into our species. As generations passed, the questions grew more sophisticated. Why did the sun follow different paths across the sky during different seasons? Why did the moon sometimes appear as a thin crescent, sometimes as a full circle, and sometimes not at all? Why did some stars appear to move among the others? Why did certain star patterns herald the coming of rains, or the migration of animals, or the best times for hunting and gathering? Answering these questions required something beyond casual observation. It demanded patience, careful record-keeping, and the development of increasingly sophisticated methods for measuring and tracking celestial motions. Slowly, astronomy was being born, not as a formal science with instruments and equations, but as a disciplined practice of watching, remembering, and passing knowledge from one generation to the next. The most dedicated sky watchers became specialists, valued members of their communities whose knowledge of celestial patterns made them essential for survival. These proto-astronomers might have been shamans or priests, elders or storytellers, but they all shared a common dedication to understanding the sky. They memorized star patterns with incredible precision, tracked subtle changes in celestial motions over decades, and developed the first systematic approaches to understanding the universe. Their tools were simple but effective. Carefully placed stones could mark the positions of sunrise and sunset at different times of year. Notched sticks could track the phases of the moon. Memory palaces, elaborate mental maps of star patterns, allowed detailed astronomical knowledge to be preserved and passed down without written language. Some of these early astronomical sites still exist today, testaments to the sophistication of our ancestors' sky watching. Stonehenge in England, with its precisely aligned stones marking solstices and eclipses, the medicine wheels scattered across the North American plains, stone circles that tracked stellar and solar cycles, the megalithic temples of Malta, oriented to specific star rises and lunar cycles. These monuments required not just observation, but mathematics, engineering, and social organization on a scale that challenges our assumptions about prehistoric civilizations. They represent the culmination of thousands of years of accumulated astronomical knowledge, passed down through oral tradition and practical application. But perhaps most remarkably, these early astronomers were developing the first theories about the nature of the cosmos. They might not have used mathematical equations or built mechanical models, but they were asking the same fundamental questions that drive astronomy today. What is the structure of the universe? How do celestial bodies move through space? What forces govern their motions? How does the cosmos relate to human existence? Their answers were often wrong by modern standards, but their questions were profound, and in asking those questions, in dedicating their lives to careful observation of the sky, they were laying the foundation for everything that would follow. Every telescope ever built, every space mission ever launched, every discovery about the nature of stars and galaxies and the expanding universe, all of it traces its ancestry back to those first humans who looked up at the night sky and wondered what they were seeing. The transition from wonder to systematic observation was gradual, taking place over thousands of years and thousands of cultures. But certain patterns emerged from this long prehistory of astronomy. The most successful early astronomers were those who combined careful observation with systematic record-keeping, who developed methods for predicting celestial events, and who found ways to pass their knowledge on to future generations. They discovered that the sky was not chaotic but orderly, that celestial motions followed patterns that could be learned and predicted, that the same laws seemed to govern both earthly and heavenly phenomena. These insights, hard-won through centuries of patient observation, represent some of humanity's first glimpses of the fundamental orderliness that underlies the apparent chaos of the natural world. And in making these discoveries, our ancestors were doing something unprecedented in the history of life on Earth. They were using their minds to explore realms far beyond their immediate physical experience. They were developing abstract concepts to explain phenomena they could observe, but not directly touch or manipulate. They were creating the first scientific theories, even if they wouldn't have recognized the term. This intellectual revolution happened quietly, around campfires and in stone circles, without fanfare or recognition. But it changed everything. It marked the moment when one species on one small planet began to reach beyond the boundaries of its immediate world toward an understanding of the cosmos itself. The questions that drove our earliest ancestors are the same questions that drive astronomy today. We still want to know what the stars are, how they move, and what our place is in the larger scheme of things. We still feel that same sense of awe when we look up at a dark sky filled with stars. We still seek patterns and relationships in the motions of celestial bodies. But we now have tools and knowledge that our ancestors could never have imagined. Where they had naked eyes and careful memory, we have telescopes that can see to the edge of the observable universe. Where they had oral traditions and stone monuments, we have written records spanning thousands of years and computer models that can simulate the evolution of galaxies over billions of years. Yet for all our technological sophistication, the fundamental human experience of astronomical wonder remains unchanged. When we look up at the night sky, whether through the eyepiece of a telescope or simply with our own eyes, we're participating in the same act of curiosity and wonder that has defined our species since its earliest days. And that continuity, that unbroken chain of human curiosity reaching from the first campfires to the launch pads of space telescopes, is perhaps the most beautiful aspect of astronomy's long history. We are the descendants of those first stargazers, carrying forward their questions and their wonder, adding our own discoveries to the accumulated knowledge of countless generations. The sky that called to our ancestors still calls to us today. The same stars that inspired the first astronomical questions still shine down on us, still invite us to wonder about our place in the cosmos. And in that shared experience of looking up and wondering, we connect not just with the universe around us, but with the deepest and most enduring aspects of human nature itself. As our earliest ancestors developed ever more sophisticated ways of watching and understanding the sky, they began to organize their observations into the first systematic astronomical traditions. These early star watchers would eventually give rise to the great astronomical civilizations of antiquity, whose careful observations and ingenious theories would lay the groundwork for all the discoveries that followed. As the centuries passed and our ancestors settled into the world's first cities, something beautiful began to happen. The casual stargazing of nomadic peoples evolved into something more systematic, more ambitious, more precise. In the fertile river valleys of Mesopotamia, along the banks of the Nile, in the mountain observatories of ancient China, dedicated sky watchers began to transform the ancient human habit of looking up into the first true science. These weren't just curious individuals anymore, but entire civilizations organizing their knowledge, building institutions, and dedicating vast resources to understanding the heavens. What had begun around campfires had grown into an enterprise involving royal astronomers, elaborate temples and mathematical systems that could predict celestial events years into the future. The story of organized astronomy begins in a land between two rivers, in what we now call Iraq. Here, in the cities of ancient Babylon, lived perhaps the most dedicated and systematic sky watchers the world had ever seen. Imagine walking through the streets of Babylon around 500 BCE. The city rises from the plain like a mountain of mud brick and glazed tile, its famous hanging gardens cascading down terraced walls, the great ziggurat temple dominating the skyline like a stepped pyramid, reaching toward the stars. But it's not just the architecture that makes this city remarkable. It's what happens here every night as darkness falls. On the flat rooftops of temples and palaces, small groups of robed figures gather around simple but effective instruments. They have no telescopes, those won't be invented for another 2,000 years, but they have something equally valuable: patience, precision, and an obsessive dedication to recording every detail of what they observe. These are the Babylonian astronomers, and they are creating something unprecedented in human history, a mathematical science of the sky. Night after night, year after year, generation after generation, they watch and record the position of the moon against the background stars, the wandering paths of the planets through the constellations, the precise times when stars rise and set, the subtle variations in the length of daylight throughout the year. Every observation is carefully noted on clay tablets using their wedge-shaped cuneiform script, creating an astronomical database that will span centuries. What makes the Babylonians unique isn't just their dedication to observation, but their approach to understanding what they see. Unlike earlier stargazers, who might have been content with recognizing patterns, the Babylonians want to measure everything. They divide the sky into precise sections, develop sophisticated mathematical techniques for tracking celestial motions, and most remarkably, they begin to predict future astronomical events with stunning accuracy. Their greatest achievement is perhaps their understanding of eclipse cycles. Lunar eclipses, those mysterious times when Earth's shadow darkens the full moon, had terrified people for thousands of years. Many cultures saw them as cosmic battles between good and evil, times when demons were devouring the moon. But the Babylonians, through centuries of careful observation, discover something wonderful. Eclipses follow predictable patterns. They realize that lunar eclipses occur roughly every 18 years, 11 days, and 8 hours in a cycle they call the Saros. With this knowledge, they can predict eclipses decades in advance, transforming terrifying supernatural events into predictable natural phenomena. Imagine the power this gave them, the ability to tell a king exactly when the moon would be darkened to the very hour. But the Babylonians don't stop with eclipses. They track the complex motions of the planets with mathematical precision that won't be surpassed for over 1,000 years. They notice that while planets generally move eastward against the background stars, they sometimes loop backward in what we now call retrograde motion. Rather than dismissing these apparent reversals as chaotic, they develop mathematical models to predict exactly when each planet will begin and end its backward dance. Their mathematical astronomy is remarkably sophisticated. Using only arithmetic, they haven't yet invented algebra or geometry in the forms the Greeks will develop. They create computational systems that can predict planetary positions with remarkable accuracy. They develop the first mathematical theory of lunar motion, accounting for the variations in the moon's speed as it orbits Earth. Perhaps most importantly for the future of astronomy, they develop the zodiac, the band of 12 constellations through which the sun, moon, and planets appear to move. This isn't just an arbitrary division of the sky, but a coordinate system that allows precise measurement of celestial positions. When they say Mars is in the middle of the lion, they're not being poetic. They're giving a precise location that any trained astronomer can understand. The Babylonians also give us our system of measuring time and angles. They divide the circle into 360 degrees, the hour into 60 minutes, the minute into 60 seconds. Every time you check a clock or use a compass, you're using a system invented by Babylonian astronomers over 2,000 years ago. But perhaps most remarkably, the Babylonians developed the first true mathematical models of celestial motion. These aren't just descriptive accounts of what they see, but predictive tools that can calculate where planets will be at any time in the past or future. They're doing mathematical astronomy, using numerical methods to unlock the secrets of celestial motion. Their influence spreads far beyond Mesopotamia. Their astronomical knowledge travels along trade routes to Egypt, Greece, and India, carrying with it both observational data and mathematical techniques that will shape astronomy for centuries to come. When Greek astronomers begin developing their own theories of celestial motion, they build upon foundations laid by these patient Babylonian sky watchers. Yet for all their mathematical sophistication, the Babylonians remain practical astronomers. Their work is motivated not by abstract curiosity alone, but by the needs of their civilization. They need accurate calendars for agricultural and religious purposes. They need to predict eclipses and other celestial events that might affect royal decision-making. They need to understand the relationship between earthly events and heavenly signs. As Babylonian astronomy reaches its mathematical heights, something different is happening far to the west, along the shores of the Mediterranean. Here, in the Greek-speaking cities of the ancient world, astronomers are developing an entirely different approach to understanding the cosmos, one based not just on mathematical prediction, but on physical models and geometric reasoning. The Greeks inherit much of their basic astronomical knowledge from the Babylonians. They learn about eclipse cycles, planetary periods, and mathematical techniques for calculating celestial positions. But they add something uniquely their own, the desire to understand not just when things happen in the sky, but why they happen. Greek astronomy begins with a revolutionary idea proposed by philosophers in the 6th century BCE. The cosmos operates according to natural laws that human reason can discover. This might seem obvious to us now, but it was a radical departure from earlier thinking. Instead of attributing celestial events to the whims of gods or supernatural forces, the Greeks proposed that the universe is a rational, orderly system that can be understood through careful thought and observation. One of the first great Greek astronomers is Thales of Miletus, who around 585 BCE supposedly predicts a solar eclipse that occurs during a battle between the Lydians and Medes. Whether this story is literally true or not, it represents something important. The Greeks' confidence that human intelligence can unlock the secrets of the cosmos. But it's with the work of later Greek astronomers that we see the full flowering of their geometric approach to understanding the heavens. Eudoxus of Cnidus, working around 370 BCE, develops the first comprehensive geometric model of planetary motion. He imagines each planet attached to a system of rotating spheres, with their combined motions accounting for the complex paths planets trace across the sky. This is revolutionary thinking. Instead of simply calculating where planets will be, as the Babylonians do, Eudoxus is trying to understand the mechanism behind their motions. He's building a physical model of the cosmos, using geometry to explain why planets move as they do. Aristotle, perhaps the most influential of all ancient philosophers, takes these ideas even further. He develops a complete cosmological system with Earth at the center, surrounded by a series of crystalline spheres carrying the moon, sun, planets, and stars. It's an elegant, rational universe where every motion has a purpose and every celestial body has its proper place. But perhaps the most remarkable achievement of Greek astronomy comes in the 3rd century BCE with the work of Aristarchus of Samos. Using geometric reasoning and careful observations, he attempts something extraordinary, measuring the relative sizes and distances of the sun and moon. Aristarchus realizes that during a half moon the sun, earth and moon form a right triangle. By measuring the angle between the sun and moon at this moment, he can calculate their relative distances using geometry. His measurements aren't very accurate. The required angle is extremely difficult to measure precisely with ancient instruments, but his method is brilliant. From his calculations, Aristarchus reaches an astonishing conclusion. The sun is much larger than Earth, and if the sun is larger than Earth, he reasons, wouldn't it make more sense for Earth to orbit the sun rather than the other way around? With this insight, Aristarchus proposes the first known heliocentric model of the solar system, nearly 1,800 years before Copernicus. He suggests that Earth rotates on its axis and orbits the sun, with the other planets doing likewise. It's a beautiful theory, elegant and mathematically sound, but it's too radical for its time. Most Greek astronomers reject it, partly because it seems to contradict everyday experience, and partly because it raises troubling questions about Earth's place in the cosmos. The mainstream of Greek astronomy continues to develop Earth-centered models of increasing sophistication. Hipparchus, working in the 2nd century BCE, makes astronomical observations of extraordinary precision. He discovers the precession of the equinoxes, a slow wobble in Earth's axis that takes 26,000 years to complete, by comparing his observations with those made by earlier astronomers. Hipparchus also develops the first accurate star catalogue, listing the positions and brightnesses of over 800 stars. He invents the magnitude system for measuring stellar brightness that we still use today, and he refines the geometric models of lunar and solar motion to a degree of accuracy that won't be improved upon for over 1,000 years. But the culmination of Greek astronomy comes with Claudius Ptolemy, working in Alexandria around 150 CE. Ptolemy inherits centuries of Greek geometric reasoning and Babylonian mathematical astronomy, and he synthesizes them into the most complete and accurate astronomical system the ancient world had ever seen. Ptolemy's great work, the Almagest, presents a comprehensive Earth-centered model of the cosmos that can predict the positions of sun, moon, and planets with remarkable precision. His key innovation is the use of epicycles, small circles whose centers move along larger circles to account for the complex motions of the planets. It's an ingenious solution to a difficult problem. The planets don't move at constant speeds in simple circles around Earth, but Ptolemy shows that their actual motions can be reproduced by combining circular motions of different sizes and periods. His model is mathematically elegant and observationally accurate, capable of predicting planetary positions centuries into the future. The Ptolemaic system will dominate Western astronomy for nearly 1,400 years, not because astronomers are afraid to challenge it, but because it works so well. It successfully predicts eclipses, planetary conjunctions, and the changing positions of celestial bodies with an accuracy that meets all practical needs of its time. Yet Ptolemy's achievement rests on a foundation that includes contributions from beyond the Greek world. Alexandria, where he works, is a cosmopolitan city where knowledge from many cultures mingles and cross-fertilizes. Among the traditions that enrich Greek astronomy is one that develops independently on the far side of the world, the astronomical heritage of ancient China. Chinese astronomy develops along a path quite different from either Babylonian or Greek traditions, yet it achieves insights and accuracies that are in many ways superior to anything developed in the West. From the earliest historical records, Chinese astronomers demonstrate a commitment to precise observation and careful record-keeping that rivals even the Babylonians. What makes Chinese astronomy unique is its integration with Chinese philosophy and statecraft. To the Chinese, the heavens are not separate from earthly affairs but intimately connected to them. The emperor rules by the mandate of heaven, and unusual celestial events are interpreted as signs of divine approval or disapproval of imperial policies. This means that Chinese astronomers operate under enormous pressure to observe and interpret celestial phenomena accurately. A missed comet or incorrectly predicted eclipse could be seen as evidence that the emperor has lost heaven's favour, potentially leading to rebellion and dynastic change. Chinese astronomical records are therefore maintained with a precision and continuity unmatched anywhere else in the ancient world. The Chinese developed their own sophisticated calendar systems, often more accurate than those used in the West. They track the motions of the planets with care, though they develop different names and mythologies for them. What the Greeks call Aries and the Romans call Mars, the Chinese call the fire star. Their observations of planetary motions are often more precise than contemporary Western records. Chinese astronomers excel particularly in observing and recording transient phenomena, comets, novae, and other unexpected celestial events that Greek astronomy often treats as anomalies. Chinese records preserve observations of supernova that provide crucial data for modern astronomers studying stellar evolution. They track comets with systematic precision, building up records that allow them to recognize periodic returns of the same objects. One of the most remarkable achievements of Chinese astronomy is their accurate measurement of the year's length. By the 1st century BCE, Chinese astronomers determined that the tropical year, the time it takes for the seasons to repeat, is 365.25 days, a figure that won't be improved upon in the West for over 1,000 years. Chinese astronomers also develop sophisticated mechanical devices for tracking celestial motions. They build elaborate clockwork mechanisms that automatically track the movements of stars and planets, creating the first mechanical computers designed for astronomical calculation. These devices combine precise metalworking with sophisticated gear trains to produce automated astronomical instruments of remarkable complexity. Perhaps most importantly, Chinese astronomy develops a tradition of continuous, systematic observation that spans over 2 millennia. Chinese astronomical records preserved in official dynastic histories provide modern astronomers with the longest continuous record of celestial phenomena available from any culture. When contemporary astronomers want to study the long-term behavior of variable stars or track the historical returns of comets, they often turn to Chinese astronomical records for data stretching back over 2,000 years. The Chinese also develop unique insights into the nature of the cosmos. They propose that the universe is infinite in extent and eternal in duration, ideas that won't appear in Western astronomy until much later. They understand that the Milky Way is composed of countless distant stars, an insight that European astronomers won't reach until the invention of the telescope. Yet despite their sophisticated observations and insights, Chinese astronomy remains largely isolated from the Babylonian and Greek traditions that dominate Western astronomical thinking. The Silk Road carries some astronomical knowledge between East and West, but the great syntheses of ancient astronomy, the works of Ptolemy, for example, develop with little input from Chinese traditions. This isolation means that many Chinese astronomical discoveries remain unknown to Western astronomers for centuries. When Jesuit missionaries arrive in China in the 16th and 17th centuries, they're astonished to discover Chinese astronomical records and instruments that in many cases surpass anything available in Europe. The synthesis of these different astronomical traditions, Babylonian mathematical precision, Greek geometric reasoning, and Chinese observational accuracy, will eventually contribute to the astronomical revolution of the Renaissance and early modern period. But that synthesis lies far in the future. For now, in the closing centuries of the ancient world, astronomy has achieved remarkable sophistication. Babylonian astronomers can predict eclipses decades in advance using purely mathematical methods. Greek astronomers have developed comprehensive geometric models that explain the complex motions of planets. Chinese astronomers maintain observational records of unprecedented accuracy and continuity. Yet each tradition also faces limitations that will eventually require new approaches to overcome. Babylonian astronomy, for all its mathematical sophistication, lacks a physical understanding of why celestial bodies move as they do. Greek astronomy, despite its elegant geometric models, sometimes sacrifices observational accuracy to theoretical elegance. Chinese astronomy, while observationally superior in many ways, remains tied to philosophical and political frameworks that sometimes inhibit theoretical development. The astronomical knowledge accumulated by these ancient civilizations represents humanity's first systematic attempt to understand the cosmos. Their observations, theories, and mathematical techniques will provide the foundation upon which all later astronomy is built. Their patient sky-watching and careful reasoning mark the transformation of casual wonder into disciplined science. As the ancient world gives way to medieval civilizations, the astronomical heritage of Babylon, Greece, and China will face new challenges and opportunities. Islamic scholars will preserve and extend Greek astronomical learning while adding new insights of their own. European monasteries will maintain astronomical knowledge through the Dark Ages. The great libraries of Baghdad and Cordoba will become centers where astronomical traditions from different cultures meet and cross-fertilize. But the patient observations and careful reasoning of ancient astronomers have already accomplished something remarkable. They have shown that human intelligence can unlock the secrets of the cosmos. The sky that once seemed chaotic and unpredictable has revealed itself to be orderly and mathematical. The universe that once seemed to operate by supernatural whim has shown itself to follow natural laws that human minds can discover and understand. This transformation of humanity's relationship with the cosmos, from fearful superstition to confident investigation, represents one of the great intellectual achievements in human history. And it all began with people looking up at the night sky and refusing to accept that its mysteries were beyond human understanding. The ancient stargazers have given us more than astronomical knowledge. They have given us confidence in human reason, faith in the orderliness of nature, and the tools and techniques that will eventually allow us to reach for the stars themselves. Their legacy will inspire and guide astronomers for centuries to come, as the gentle questioning that began around campfires continues to drive humanity's greatest intellectual adventure. As the Roman Empire faded into history and Europe entered what historians once called the Dark Ages, it might seem that the flame of astronomical knowledge would flicker and die. The great libraries of Alexandria were closing, the philosophical schools of Athens were shuttering their doors, and much of the astronomical wisdom accumulated over centuries seemed destined to be lost forever. But knowledge, like starlight itself, has a way of travelling vast distances and illuminating unexpected places. Far from dying out, astronomical learning was about to enter one of its most brilliant and productive periods, flourishing in the libraries and observatories of a rapidly expanding Islamic civilization that stretched from Spain to Central Asia. Picture Baghdad in the year 800 CE. The city rises from the banks of the Tigris River like a jewel of learning and commerce, its round walls enclosing a cosmopolitan metropolis where scholars from across the known world gather to study, translate, and expand human knowledge. In the House of Wisdom, one of history's greatest centres of learning, translators work by lamplight to render Greek, Persian, and Sanskrit texts into Arabic, preserving and transmitting the astronomical heritage of ancient civilizations. Here, patient scribes are copying the works of Ptolemy, transforming his Greek Almagest into Arabic as the Kitab al-Majisti. But they're doing far more than simply preserving ancient knowledge. They're questioning it, testing it, and finding ways to improve upon it. Islamic astronomy is about to embark on a period of innovation that will revolutionize humanity's understanding of the cosmos. The Islamic approach to astronomy grows from a unique combination of practical necessity and intellectual curiosity. The religious obligations of Islam create immediate astronomical needs, determining the precise times for daily prayers, finding the direction to Mecca from any location on Earth, and establishing an accurate calendar for religious observances. But Islamic scholars don't simply seek to meet these practical requirements. They use them as springboards for comprehensive investigations into the nature of the cosmos. One of the first great Islamic astronomers is al-Battani, working in the 9th and 10th centuries in what is now Syria. Al-Battani doesn't simply accept Ptolemy's measurements and calculations. He sets out to verify them through his own careful observations. Using improved instruments and more precise techniques, he discovers that Ptolemy's values for the length of the year and the precession of the equinoxes contain small but significant errors. Al-Battani's corrected value for the length of the year is accurate to within minutes of the true value, representing a dramatic improvement over Ptolemy's figure. His measurements of the precession of the equinoxes, that slow wobble in Earth's axis discovered by the Greek astronomer Hipparchus, are so precise that they won't be bettered for centuries. But perhaps most importantly, al-Battani demonstrates that ancient astronomical knowledge, however respected, must be tested against new observations. This willingness to question and improve upon inherited wisdom becomes a hallmark of Islamic astronomy. Where earlier traditions might have accepted Ptolemy's Almagest as the final word on celestial mechanics, Islamic astronomers treat it as a starting point for further investigation. Al-Biruni, working in the 11th century, exemplifies this critical approach. He conducts systematic observations to test Ptolemaic theory, develops new methods for measuring the Earth's circumference, and writes extensively on astronomical methodology. Al-Biruni understands that precise observation requires precise instruments, and he devotes considerable effort to improving astronomical tools and techniques. His measurement of Earth's circumference, conducted by carefully observing the angle of a mountain peak from two different elevations, yields a result accurate to within a few % of the true value. More importantly, his method demonstrates the power of combining mathematical reasoning with careful measurement, principles that will become central to the scientific revolution centuries later. But perhaps the most revolutionary contributions of Islamic astronomy come in the realm of planetary theory. While Ptolemy's epicycle models could predict planetary positions with reasonable accuracy, they contained certain features that troubled Islamic astronomers on both philosophical and mathematical grounds. The Ptolemaic system required that some planetary motions be measured not from the center of their circular orbits, but from a point called the equant, an imaginary location offset from the center. This mathematical device made the models work better observationally, but it violated Aristotelian principles of uniform circular motion that most medieval astronomers accepted as fundamental. Islamic astronomers set themselves an extraordinary challenge: develop planetary models that could match Ptolemy's predictive accuracy while eliminating the troublesome equant point and restoring uniform circular motion. This might seem like an abstract theoretical problem, but it drives some of the most sophisticated mathematical astronomy ever attempted. Ibn al-Shatir, working in Damascus in the 14th century, develops an ingenious solution using what he calls the double epicycle, a system where planets move on small circles whose centers move on other small circles, which in turn revolve around larger circles. His models are mathematically elegant and philosophically satisfying, eliminating the equant while maintaining predictive accuracy. Even more remarkably, Islamic astronomers at the Marageh Observatory in Persia develop planetary models that are mathematically equivalent to those that Copernicus will propose 2 centuries later. These Islamic astronomers don't take the final step of placing the sun at the center of their system, but their mathematical techniques for describing planetary motion are virtually identical to those Copernicus will use in his revolutionary heliocentric model. The Marageh Observatory itself represents something new in the history of astronomy, a large-scale, well-funded institution dedicated entirely to astronomical research. Founded in 1259 under the patronage of the Mongol ruler Hulagu Khan, it brings together astronomers from across the Islamic world and beyond, creating an international center for astronomical study that won't be matched in Europe for centuries. At Marageh, astronomers work with instruments of unprecedented size and precision. Their astrolabes, armillary spheres and quadrants are marvels of metalworking and mathematical design, allowing observations accurate to fractions of a degree. The observatory's main building houses a library containing thousands of astronomical works, while nearby workshops produce the specialized instruments needed for cutting-edge research. The collaborative approach developed at Marageh produces astronomical tables of remarkable accuracy. The Ilkhanic tables, compiled under the direction of Nasir al-Din al-Tusi, provide predictions of planetary positions that are significantly more accurate than any available in medieval Europe. These tables will eventually reach European astronomers and contribute to the growing dissatisfaction with Ptolemaic astronomy that will fuel the Copernican revolution. Islamic astronomers also make crucial contributions to observational technique and instrument design. Al-Zarqali, working in 11th century Cordoba, develops the Saphia, an improved astrolabe that can be used at any latitude, making accurate astronomical observation possible throughout the Islamic world. His Toledan tables become the standard astronomical reference for centuries, spreading from Islamic Spain throughout Europe. The astrolabe itself, while invented in ancient Greece, reaches its highest development in Islamic hands. Islamic craftsmen create astrolabes of extraordinary beauty and precision, combining mathematical sophistication with artistic elegance. These instruments serve not only for astronomical calculation, but also for navigation, timekeeping, and religious observance. Islamic astronomers understand that accurate observations require understanding atmospheric effects on starlight. Al-Hazen, known in the West as Al-Hazen, conducts the first systematic studies of atmospheric refraction, the bending of light as it passes through Earth's atmosphere. His work explains why stars appear to twinkle and why the sun appears flattened when near the horizon, laying foundations for optics that will eventually lead to the invention of the telescope. The influence of Islamic astronomy extends far beyond the Islamic world itself. As Christian armies reconquer Islamic territories in Spain, they discover libraries filled with astronomical works of unprecedented sophistication. Translation centers in cities like Toledo become crucial conduits for transmitting Islamic astronomical knowledge to medieval Europe. The process of translation reveals the extent to which Islamic astronomers have advanced beyond their ancient predecessors. European scholars translating Arabic astronomical works discover not just preserved Greek knowledge, but entirely new theories, improved observations, and sophisticated mathematical techniques that are centuries ahead of contemporary European astronomy. Alfonso X of Castile, recognizing the superiority of Islamic astronomical knowledge, commissions the Alphonsine tables in the 13th century, based largely on the work of Al-Zarqali and other Islamic astronomers. These tables will dominate European astronomy for over 300 years, providing the most accurate available predictions of planetary positions until the time of Copernicus. The transmission of Islamic astronomical knowledge to Europe occurs through multiple channels. Returning crusaders bring back astronomical instruments and texts. Jewish scholars working within both Islamic and Christian contexts serve as cultural bridges transmitting astronomical knowledge. The School of Translators in Toledo systematically renders Arabic astronomical works into Latin, making them available to European scholars. But the influence flows in more subtle ways as well. The very idea that ancient astronomical knowledge can be questioned and improved, so central to Islamic astronomy, gradually takes root in European thinking. The critical, observational approach developed by Islamic astronomers provides a model for the empirical methods that will eventually characterize the scientific revolution. Perhaps most importantly, Islamic astronomy preserves and transmits the mathematical tools that will prove essential for later astronomical advances. Islamic mathematicians significantly advanced trigonometry, developing techniques for spherical trigonometry that are crucial for astronomical calculation. Their work on algebra and geometric methods provides the mathematical foundation upon which Copernicus, Kepler, and Newton will build their revolutionary theories. The decline of Islamic astronomy in the later medieval period results not from any inherent limitations in Islamic approaches to science, but from political and economic factors that redirect resources away from astronomical research. The Mongol invasions, the Black Death, and political fragmentation disrupt the institutional framework that had supported astronomical investigation. But by this time, the torch of astronomical knowledge has been passed to a new generation of European scholars who build directly upon Islamic foundations. When Copernicus develops his heliocentric theory, he explicitly acknowledges his debt to Islamic astronomers. When European instrument makers begin producing sophisticated astronomical tools, they adapt techniques pioneered in Islamic workshops. The legacy of Islamic astronomy extends far beyond its specific discoveries and innovations. Islamic astronomers establish new standards for observational precision, develop institutional frameworks for collaborative research, and demonstrate that human knowledge of the cosmos can continue to advance through careful observation and mathematical reasoning. They show that astronomy is truly a universal human enterprise, transcending cultural and religious boundaries. The same desire to understand the cosmos that motivated ancient Babylonians and Greeks finds new expression in Islamic civilization, producing advances that benefit all of humanity. Most importantly, Islamic astronomers maintain the tradition of questioning received wisdom that is essential to scientific progress. They demonstrate that even the most respected authorities, whether Ptolemy, Aristotle, or other ancient masters, must be tested against observation and improved upon when necessary. This critical spirit, combined with sophisticated mathematical techniques and precise observational methods, creates the foundation upon which the astronomical revolution of the Renaissance will build. When European astronomers begin questioning the Earth-centered cosmos in the 15th and 16th centuries, they will use tools, techniques, and mathematical methods developed in Islamic observatories and libraries. The gentle arc of human curiosity that began around ancient campfires continues its journey through the medieval period, enriched and advanced by Islamic civilization's commitment to learning and discovery. The stars that called to our earliest ancestors speak now with mathematical precision to scholars working by lamplight in Baghdad, Cordoba, and Maragha, their observations and calculations preparing the way for even greater revelations to come. As Islamic astronomy reaches its zenith in the great observatories of the medieval period, new stirrings of astronomical curiosity begin to emerge in the universities and courts of Renaissance Europe. The preserved and enhanced wisdom of the ancients, filtered through centuries of Islamic scholarship, is about to encounter a new generation of European thinkers ready to question the very foundations of cosmic understanding. In the quiet cathedral town of Frombork, along the Baltic coast of what is now Poland, an elderly canon spends his final years working on a manuscript that will change everything. Nicholas Copernicus, physician, mathematician, and church administrator, has devoted decades to a troubling question. Why do the mathematical models that predict planetary motions work so well, yet seem to describe a universe that makes no physical sense? It's the early 16th century, and European astronomy is experiencing a quiet crisis of confidence. The Ptolemaic system, refined by Islamic astronomers and transmitted through medieval universities, can predict eclipses and planetary positions with reasonable accuracy. But the models have grown increasingly complex, requiring dozens of circles upon circles to account for the observed motions of planets. More troubling still, different astronomical tables often give conflicting predictions for the same celestial events. Copernicus has access to the best astronomical knowledge of his time. He has studied at the University of Krakow, travelled to Italy to learn from the finest scholars of the age, and absorbed both the classical tradition of Ptolemy and the improvements developed by Islamic astronomers. Yet the more deeply he studies the mathematical astronomy of his era, the more convinced he becomes that something is fundamentally wrong with humanity's picture of the cosmos. The problem isn't simply mathematical, it's philosophical. The Ptolemaic system places Earth at the centre of the universe, but it requires planetary motions that seem arbitrary and unnecessarily complicated. Why should Mars sometimes loop backward against the stars? Why should Venus and Mercury never stray far from the Sun? Why should the speed of planetary motion vary in such complex ways? In the solitude of his study, surrounded by astronomical tables and geometric diagrams, Copernicus begins to explore a radical possibility. What if Earth is not the motionless centre of the universe? What if it is simply another planet, orbiting the Sun along with Mars, Venus, and the rest? The idea isn't entirely new. Copernicus knows that Aristarchus of Samos proposed a sun-centered system in ancient times, and he's familiar with Islamic astronomical works that explore alternatives to strict Ptolemaic orthodoxy. But what Copernicus proposes to do is work out the mathematical details of a heliocentric system with the same precision that Ptolemy brought to his Earth-centered models. As he develops his theory, Copernicus discovers something beautiful. Placing the Sun at the centre eliminates many of the arbitrary features that make the Ptolemaic system so unsatisfying. The retrograde motion of Mars becomes a natural consequence of Earth, overtaking the more distant planet in its orbit, like a faster runner lapping a slower one on a circular track. The fact that Venus and Mercury stay close to the Sun becomes obvious. They orbit closer to the Sun than Earth does. More importantly, the heliocentric system reveals a natural order in the solar system. The planets arrange themselves by distance from the Sun. Mercury, Venus, Earth, Mars, Jupiter, Saturn. Their periods of revolution increase with their distance from the Sun, following a simple rule that suggests underlying physical harmony rather than arbitrary mathematical convenience. Yet Copernicus hesitates to publish his theory. He understands that placing Earth in motion contradicts both common sense and religious teaching. If Earth spins on its axis, why don't we feel the motion? If Earth rushes through space in its orbit around the Sun, why don't the stars shift position as our viewpoint changes? These aren't trivial objections. They point to real physical questions that won't be fully answered for centuries. Copernicus spends decades refining his system, trying to make it as mathematically precise as the Ptolemaic models it aims to replace. He retains many features of ancient astronomy, including the assumption that all celestial motions must be combinations of uniform circular motion. His final system still requires epicycles, though fewer than Ptolemy's, and his predictions of planetary positions aren't dramatically more accurate than existing tables. De Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres, finally appears in 1543, reportedly placed in Copernicus's hands as he lay on his deathbed. The work presents a complete mathematical astronomy based on the radical premise that Earth is a planet orbiting the Sun. It's a technical treatise, filled with geometric diagrams and numerical tables, but its implications extend far beyond astronomy. The initial reaction to Copernican astronomy is more puzzled than outraged. Most astronomers recognize the mathematical elegance of the heliocentric system, but they question whether it describes physical reality or merely provides a convenient calculating device. The preface to the first edition, written by Andreas Osiander without Copernicus's permission, suggests that astronomical theories should be judged only on their ability to predict celestial motions, not on their truth as descriptions of cosmic structure. This instrumentalist interpretation allows Copernican astronomy to spread gradually through European universities without immediate religious controversy. Astronomers use Copernican techniques to improve calendar calculations and planetary tables, while remaining agnostic about whether the Sun really stands still and Earth really moves. But a new generation of astronomers emerges who take the physical reality of the heliocentric system seriously. Chief among them is Tycho Brahe, a Danish nobleman whose approach to astronomy combines the theoretical sophistication of the Renaissance with an observational precision that surpasses anything achieved in the ancient or medieval world. Tycho's passion for astronomy begins dramatically. As a young student, he witnesses a partial solar eclipse and is amazed to discover that existing astronomical tables predict the event incorrectly by nearly a day. This experience convinces him that astronomy needs better observations, not just better theories. If astronomers are to understand the true structure of the cosmos, they must first measure celestial motions with unprecedented accuracy. Tycho persuades King Frederick II of Denmark to fund an extraordinary project, the construction of Uraniborg, a research institute dedicated entirely to astronomical observation. Built on the island of Hven in the Danish Sound, Uraniborg becomes Europe's first major astronomical observatory, equipped with instruments of Tycho's own design that achieve accuracy measured in fractions of a degree. For 20 years, Tycho and his assistants conduct systematic observations of planetary motions, stellar positions, and celestial phenomena. They track the planets night after night, season after season, building up a database of observations more precise and comprehensive than any previously assembled. Tycho's measurements of planetary positions are accurate to within 2 arc minutes, about 1/30th the width of the full moon, an achievement that won't be significantly improved upon until the invention of the telescope. Tycho's observations reveal that Copernicus, while correct about the basic structure of the solar system, was wrong about many details. The planets don't move in perfect circles at constant speeds, as both Ptolemy and Copernicus had assumed. Their actual motions are more complex, following patterns that no combination of uniform circular motions can reproduce exactly. These discrepancies might seem like minor technical problems, but they point toward a fundamental revolution in how astronomers think about celestial motion. The ancient assumption that heavenly bodies must move in perfect circles begins to crumble under the weight of precise observation. The cosmos, as revealed by Tycho's measurements, is more complex and less geometrically perfect than anyone had imagined. Tycho himself proposes a compromise system that attempts to preserve the best features of both Ptolemaic and Copernican astronomy. In the Tychonic system, the Sun and Moon orbit Earth, while the other planets orbit the Sun. This geocentric-heliocentric hybrid explains many of the same phenomena as the Copernican system, while avoiding the troublesome implications of a moving Earth. But Tycho's greatest contribution to astronomy isn't his theoretical system, it's his 20 years of precise observations. When Tycho dies in 1601, his observational data passes to his former assistant Johannes Kepler, a German mathematician and astronomer who will use Tycho's measurements to solve the puzzle of planetary motion once and for all. Kepler approaches astronomy with a mystical conviction that mathematical harmony underlies all cosmic phenomena. He believes that God created the universe according to geometric principles that human reason can discover, and he sets out to find the mathematical laws that govern planetary motion. This search will occupy him for decades and lead to discoveries that transform humanity's understanding of the cosmos. Working with Tycho's observations of Mars, Kepler tries to construct a model that can predict the planet's position with the accuracy that Tycho's measurements demand. He discovers that no combination of circular motions can reproduce Mars's actual path to within the precision of Tycho's data. The discrepancies are small, often less than 8 arc minutes, but they're consistent and undeniable. After years of calculation, Kepler makes a revolutionary decision. He abandons the ancient assumption that planetary motions must be combinations of perfect circles. Instead, he discovers that Mars follows an elliptical orbit with the Sun at one focus of the ellipse. This simple geometric insight immediately resolves the discrepancies that had plagued astronomers for centuries. Kepler's first law of planetary motion, that planets move in elliptical orbits, represents a fundamental break with the circular perfection that had dominated astronomical thinking since ancient times. But his second law is even more revolutionary. Planets move faster when they're closer to the Sun and slower when they're farther away, sweeping out equal areas in equal times. These laws transform astronomy from a geometric exercise in combining circular motions into a study of dynamical relationships between celestial bodies. Kepler shows that planetary motion follows precise mathematical rules, but they're laws of physics rather than geometry, laws that relate the motion of planets to their distances from the Sun. Kepler's third law, discovered years later, reveals an even deeper harmony. The square of a planet's orbital period is proportional to the cube of its average distance from the Sun. This relationship, connecting the time scales of planetary motion to the spatial structure of the solar system, suggests underlying physical forces that govern celestial dynamics. The work of Copernicus, Tycho, and Kepler represents a fundamental transformation in humanity's approach to understanding the cosmos. Where ancient and medieval astronomers had been content to save the phenomena, to develop mathematical models that could predict celestial motions regardless of their physical plausibility, Renaissance astronomers begin to insist that astronomical theories must describe the actual structure and behavior of the physical universe. This shift from mathematical convenience to physical reality requires new standards of observational precision, new willingness to abandon ancient assumptions, and new mathematical techniques for analyzing natural phenomena. It marks the beginning of what we now recognize as the scientific revolution, a transformation in human knowledge that will ultimately lead to space travel and our modern understanding of the universe. The Renaissance astronomers also established new ways of validating astronomical knowledge. Where earlier traditions might have accepted theoretical systems based on their mathematical elegance or their agreement with philosophical principles, Renaissance astronomy increasingly demands that theories be tested against precise observations. This empirical approach, combining careful measurement with mathematical analysis, becomes the foundation of modern science. The instruments and techniques developed during the Renaissance, precision measurement, systematic observation, mathematical modelling, and empirical testing, create the framework within which all later astronomical discoveries will be made. When Galileo turns the newly invented telescope toward the heavens in the early 17th century, he will use these Renaissance methods to gather observational evidence that finally convinces the astronomical community that Copernicus was right about the fundamental structure of the solar system. The patient work of Renaissance astronomers, building upon the preserved wisdom of ancient civilizations and the methodological advances of Islamic scholars, has prepared the ground for a revolution in human understanding. The cosmos revealed by their observations and calculations is no longer the small, earth-centered universe of ancient tradition, but a vast system of worlds in motion, governed by mathematical laws that human intelligence can discover and understand. As the Renaissance draws to a close, astronomy stands poised for even greater revelations. The newly invented telescope is about to provide unprecedented views of celestial objects, while new mathematical techniques for analyzing motion will soon reveal the forces that govern planetary orbits and guide the paths of comets through the solar system. In the autumn of 1609, news reaches the bustling port city of Venice of a curious invention from the Low Countries, a device that can make distant objects appear closer, a tube containing lenses that Dutch spectacle makers call a looker, or spyglass. For merchants and naval commanders, the military and commercial applications are immediately obvious. But for Galileo Galilei, mathematician and natural philosopher at the University of Padua, this simple optical device represents something far more profound, humanity's first chance to see beyond the limits of naked eye observation that had constrained astronomy for thousands of years. Galileo doesn't simply acquire one of these telescopes. He sets out to understand and improve the device. Working in his study, grinding lenses and experimenting with different combinations of magnification, he creates telescopes far superior to the original Dutch models. Where the first spyglasses might magnify objects 3 or 4 times, Galileo's instruments achieve magnifications of 20 times or more, transforming fuzzy, distant images into clear, detailed views. But Galileo's true genius lies not in his technical improvements to the telescope, but in his decision to point this new instrument toward the heavens. On a clear night in late 1609, he becomes the first human being to observe celestial objects through a telescope, beginning a revolution in astronomy that will sweep away the last vestiges of ancient cosmology and establish the heliocentric system as undeniable reality. What Galileo sees through his telescope transforms everything. The moon, that familiar companion that has inspired poets and guided travellers since the beginning of human history, reveals itself to be not a smooth, perfect sphere as Aristotelian philosophy insisted, but a world of mountains and valleys, craters and plains, a landscape as rugged and varied as Earth itself. The implications are staggering. For over 1,000 years, European natural philosophy had drawn a sharp distinction between the terrestrial realm of change and decay and the celestial realm of perfection and immutability. The moon as a celestial body was supposed to be perfectly spherical and unmarked by any blemishes. Yet here, visible through Galileo's telescope, are shadows cast by lunar mountains, dark plains that might be seas, and a surface scarred by what appear to be enormous craters. Galileo carefully maps the changing patterns of shadow on the lunar surface as the moon goes through its phases, using the length and direction of shadows to calculate the heights of lunar mountains. Some peaks, he discovers, are even taller than any mountains on Earth. The moon is not a perfect celestial sphere, but a world, a place with geography, topography, and landscapes that could, in principle, be explored. But the moon is only the beginning. When Galileo turns his telescope toward Jupiter, the largest planet visible in the night sky, he makes a discovery that shakes the foundations of astronomy. Jupiter is not alone. It is accompanied by 4 smaller points of light that move in regular patterns around the giant planet. Night after night, Galileo tracks these Medicean stars, as he diplomatically names them, in honor of his potential patrons, and realizes he is witnessing something unprecedented, moons orbiting another planet. The existence of Jupiter's moons demolishes one of the strongest arguments against the Copernican system. Critics of heliocentrism had long argued that if Earth moved through space in orbit around the Sun, it would leave the moon behind. How could Earth carry the moon along in its cosmic journey? The moons of Jupiter provide a clear answer. Large bodies can indeed move through space, while retaining their satellites. If Jupiter can carry 4 moons along in its orbit around the Sun, Earth can certainly carry one. More profoundly, the Jovian moons reveal that Earth is not the only centre of circular motion in the universe. The Ptolemaic system had assumed that all celestial motions were centred on Earth, but here were 4 objects clearly orbiting around Jupiter. The cosmos, as revealed by the telescope, contains multiple centres of motion, exactly what the Copernican system predicted. When Galileo observes Venus through his telescope, he finds even more compelling evidence for the heliocentric model. Venus, he discovers, goes through a complete cycle of phases just like the moon, sometimes appearing as a thin crescent, sometimes as a full disk, sometimes as a half circle. The Ptolemaic system, which placed Venus between Earth and the Sun, could only account for crescent phases. The full range of phases that Galileo observes can only be explained if Venus orbits the Sun, sometimes appearing on the far side of the Sun from Earth, showing a full disk, and sometimes on the near side, showing a crescent. These observations provide the first direct visual evidence that at least some planets orbit the Sun rather than Earth. Combined with the moons of Jupiter, the phases of Venus make the Copernican system not just mathematically convenient, but observationally necessary. Galileo's telescopic discoveries extend beyond the solar system to the stars themselves. When he observes the Milky Way through his telescope, That faint band of light that stretches across the night sky resolves into countless individual stars, far too numerous to count. The ancient question about the nature of the Milky Way, whether it was a cosmic river, a celestial roadway, or something else entirely, finds its answer in Galileo's telescope. It is a vast collection of stars, so distant that they appear as a continuous glow to the naked eye. This discovery hints at the true scale of the universe. If the Milky Way contains countless stars, and if some of these stars might be as large and bright as the Sun but appear faint due to their enormous distance, then the cosmos is far vaster than anyone had previously imagined. The universe revealed by Galileo's telescope is not the cosy, human-sized cosmos of ancient tradition, but an almost incomprehensibly large realm filled with worlds and stars beyond number. Galileo also observes that even through his powerful telescope, the stars appear as tiny points of light rather than disks. This observation addresses another classical objection to the Copernican system. If Earth orbits the Sun, critics argued, then the stars should appear to shift position as our viewpoint changes throughout the year, an effect called stellar parallax. The absence of observable parallax was often cited as evidence against Earth's motion. Galileo's telescopic observations suggest an answer to this puzzle. If the stars are so distant that even powerful telescopes show them as mere points of light, then they must be far more distant than anyone had previously supposed. At such enormous distances, the parallax caused by Earth's orbital motion would be too small to detect with available instruments. The absence of observable stellar parallax doesn't disprove Earth's motion. It reveals the incredible vastness of space. The impact of Galileo's discoveries extends far beyond astronomy. His telescopic observations provide the first concrete evidence that the physical world contains phenomena invisible to natural human senses. The mountains of the moons of Jupiter, the phases of Venus, all of these discoveries were made possible by artificial enhancement of human vision. This insight opens the door to experimental science based on instruments and measurement rather than pure philosophical reasoning. Galileo's approach to presenting his discoveries also represents something new in the history of science. In his Sidereus Nuncius, Starry Messenger, published in 1610, he doesn't simply describe what he has seen, but provides detailed drawings and careful documentation of his observations. He invites other astronomers to build their own telescopes and verify his discoveries for themselves. This emphasis on reproducible observation becomes a cornerstone of the scientific method. The reception of Galileo's discoveries varies dramatically across different audiences. Many astronomers and natural philosophers, once they have access to telescopes and can verify Galileo's observations for themselves, quickly accept the reality of what he has discovered. The evidence is simply too clear and too easily reproduced to deny. But the implications of telescopic astronomy create profound challenges for traditional ways of understanding the cosmos. If the heavens are not perfect and immutable, if Earth is not the center of all motion, if the universe is vastly larger than previously imagined, then entire philosophical and theological systems must be reconsidered. The telescope doesn't just reveal new astronomical facts, it forces a fundamental reconsideration of humanity's place in the cosmos. Galileo's later telescopic work continues to provide evidence for the new astronomy. He observes dark spots on the surface of the Sun, tracking their movement to demonstrate that the Sun rotates on its axis. This discovery further undermines the notion of celestial perfection, while showing that the Sun, like Earth, is a rotating body. He studies Saturn and glimpses what later astronomers will recognize as its ring system. though his telescope isn't powerful enough to resolve the rings clearly. Perhaps most importantly, Galileo's telescopic program establishes observational astronomy as an experimental science. Where earlier astronomers had been limited to tracking the positions and motions of celestial objects, telescope astronomy reveals the physical characteristics of other worlds. The Moon has mountains, Jupiter has satellites, the Sun has spots, Venus has phases. All of these discoveries transform abstract points of light into physical objects with observable properties. This transformation from positional to physical astronomy opens entirely new avenues for investigation. If other planets are worlds like Earth, might they have atmospheres, seasons, weather patterns? If the Sun rotates and has spots, what does this reveal about its physical nature? If stars are distant suns, might some of them have planetary systems of their own? Galileo's work also demonstrates the power of technological innovation to drive scientific discovery. The telescope, initially developed for terrestrial applications, becomes the first of many scientific instruments that extend human senses into previously inaccessible realms. This pattern, technological innovation enabling new observations that drive theoretical breakthroughs, will characterize scientific progress for centuries to come. The controversy surrounding Galileo's support for Copernican astronomy, culminating in his trial by the Roman Inquisition in 1633, illustrates the broader cultural impact of the telescopic revolution. The new astronomy doesn't just challenge scientific theories, it threatens entire worldviews that place humanity at the center of cosmic purpose. The resistance to Galilean astronomy reflects not just religious conservatism, but the profound psychological challenge of accepting humanity's displacement from the center of the universe. Yet despite official opposition, the telescopic evidence for the Copernican system proves irresistible to the astronomical community. Within a few decades of Galileo's first observations, virtually all practicing astronomers accept that Earth orbits the Sun, and that the solar system is just one small part of a universe filled with stars and worlds. The telescope also democratizes astronomy in unprecedented ways. Where earlier astronomical knowledge had been confined to small groups of professional mathematicians and court astronomers, telescopes make the wonders of the cosmos accessible to anyone with the modest resources needed to acquire or build the instrument. Amateur astronomers begin making important discoveries, and public interest in astronomy flourishes as never before. Galileo's telescopic discoveries establish the empirical foundation upon which all later astronomy will build. His observations of the Moon inaugurate planetary science. His discovery of Jupiter's moons begins the study of satellite systems. His observations of stellar phenomena open the door to astrophysics. Every space mission, every modern telescope, every discovery about the nature of planets and stars traces its ancestry back to that moment when Galileo first pointed his small telescope toward the heavens and saw worlds that no human eye had ever beheld. The revolution begun by Galileo's telescope extends far beyond astronomy to establish new standards for all natural philosophy. The principle that theories must be tested against careful observation, that instruments can reveal truths invisible to natural human senses, that the physical world operates according to discoverable laws. All of these fundamental aspects of modern science find early expression in Galileo's telescopic work. As telescopes improve and become more widely available throughout the 17th century, they will reveal even more wonders. The rings of Saturn, the great red spot of Jupiter, the changing appearance of Mars, the discovery of new planets beyond Saturn. Each new discovery will further confirm that the cosmos revealed by Copernicus, Kepler, and Galileo is indeed the universe in which we live, a vast, dynamic realm of worlds in motion, governed by mathematical laws that human intelligence can discover and understand. But Galileo's telescopic revolution also raises new questions that will drive astronomical research for centuries to come. If the planets are worlds, what forces keep them in their orbits? If stars are distant suns, how do we measure their distances and understand their physical nature? If the universe is vastly larger than anyone had imagined, what lies in the depths of space beyond the reach of even the most powerful telescopes? These questions, inspired by the first glimpses through Galileo's simple telescope, will soon find their answers in the mathematical physics of Newton and the systematic observations of a new generation of astronomers equipped with ever more powerful instruments. In the quiet English countryside of Woolsthorpe during the plague years of 1665 and 1666, a young Cambridge scholar finds himself with an unexpected gift. Time to think. Isaac Newton, sent home from university as London battles the Great Plague, spends these months in rural solitude contemplating questions that will transform humanity's understanding of the cosmos. Here, in the garden, where legend places his famous encounter with a falling apple, Newton begins to glimpse the universal principles that govern motion, both on Earth and in the heavens. The questions that occupy Newton's mind have been troubling natural philosophers for decades. Galileo's telescopic discoveries and Kepler's laws of planetary motion have revealed what happens in the cosmos, but they haven't explained why it happens. Why do planets follow elliptical orbits? What force keeps them circling the sun rather than flying off into space? Why does the moon orbit Earth rather than falling to the ground like terrestrial objects? Newton's insight begins with a simple but profound recognition. The force that causes an apple to fall from a tree might be the same force that keeps the moon in its orbit around Earth. This isn't merely a poetic metaphor, it's a mathematical hypothesis that can be tested through calculation. If gravity extends from Earth's surface all the way to the moon, weakening with distance according to some mathematical law, then the moon's orbital motion might be simply the result of continuously falling toward Earth while moving fast enough sideways to miss it. The mathematics required to test this idea pushes Newton to develop entirely new forms of calculation, what we now call calculus. Working in isolation, he creates mathematical tools powerful enough to analyze the continuously changing motions of celestial bodies. These techniques allow him to move beyond Kepler's purely descriptive laws to uncover the underlying physical principles that make planetary motion inevitable. Newton's calculations reveal something beautiful. If gravity follows an inverse square law, becoming 4 times weaker when the distance doubles, 9 times weaker when the distance triples, then Kepler's laws emerge naturally as mathematical consequences. The elliptical orbits, the relationship between orbital period and distance, the way planets sweep out equal areas in equal times, all of these observational patterns that Kepler discovered through years of calculation become simple results of a single underlying force. But Newton doesn't stop with the Earth-Moon system, or even the solar system. His developing theory of universal gravitation suggests that every piece of matter in the universe attracts every other piece with a force that depends on their masses and the distance between them. The same force that governs planetary motion also explains the tides, the precession of Earth's axis, and countless other phenomena that had previously seemed unrelated. When Newton finally publishes his Principia Mathematica in 1687, it presents not just a theory of gravity, but an entirely new way of understanding the physical world. The universe revealed by Newton's mathematics is a clockwork cosmos, where every motion from the fall of a stone to the orbit of a comet follows precise mathematical laws that can be calculated with perfect accuracy. The implications extend far beyond astronomy. If the universe operates according to mathematical laws, then human reason can in principle understand any natural phenomenon by discovering the equations that govern it. Newton's success in explaining celestial mechanics through mathematical physics becomes the model for all subsequent scientific investigation. Newton's gravitational theory also provides the first satisfactory explanation for tidal phenomena. The twice-daily rise and fall of ocean levels had puzzled natural philosophers for centuries. Some attributed tides to the breathing of a cosmic whale, others to underground fires or atmospheric pressure. Newton shows that tides result naturally from the differential gravitational attraction of the Moon and Sun on Earth's oceans. The same force that governs planetary motion also shapes the rhythm of terrestrial seas. The precision of Newton's predictions astonishes contemporary astronomers. His calculations explain not just the general behavior of planets, but subtle effects that previous theories couldn't account for. The slow rotation of Mercury's orbit, the complex motion of the Moon, the way Earth's axis wobbles over thousands of years. All of these phenomena emerge from Newton's mathematics as inevitable consequences of gravitational interaction. Perhaps most remarkably, Newton's theory allows astronomers to work backward from observed motions to deduce the existence of unseen gravitational influences. When comet orbits deviate slightly from calculated paths, astronomers can infer the gravitational effects of planets too distant to be easily observed. This predictive power transforms astronomy from a descriptive science into an investigative tool capable of discovering hidden aspects of the cosmos. The study of comets becomes a proving ground for Newtonian mechanics. These mysterious visitors, appearing unpredictably in the night sky and often inspiring fear and superstition, reveal themselves to be regular members of the solar system following predictable elliptical orbits. Edmund Halley, Newton's friend and supporter, uses gravitational theory to calculate the orbit of the comet that now bears his name, predicting its return in 1758, a prediction vindicated decades after both Newton's and Halley's deaths. This successful prediction of Halley's comet return provides dramatic confirmation of Newtonian physics while demonstrating astronomy's new predictive power. The ability to foretell the precise return of a celestial visitor transforms public perception of astronomy from medieval astrology to modern science. Comets become natural phenomena governed by comprehensible laws rather than supernatural omens of disaster. The application of gravitational theory to comet orbits also reveals the true scale of the solar system. Some comets follow such elongated ellipses that they venture far beyond the orbit of Saturn, taking centuries to complete their journeys around the Sun. These orbital calculations provide the first reliable measurements of distances in the outer solar system, showing that the realm of the Sun's gravitational influence extends much farther than anyone had previously imagined. Newton's work also stimulates the search for new worlds within the solar system. If gravity governs all celestial motion, then careful observation of planetary movements should reveal gravitational perturbations caused by undiscovered objects. This reasoning leads to the systematic mapping of the outer solar system and the discovery of worlds beyond the classical planets known to ancient astronomers. The discovery of Uranus in 1781 by William Herschel exemplifies the new observational astronomy made possible by improved telescopes and Newtonian theory. Herschel, a musician turned astronomer, initially mistakes the distant world for a comet, but careful tracking of its motion reveals a nearly circular orbit far beyond Saturn. Uranus becomes the first planet discovered in the telescopic age, doubling the known size of the solar system at a stroke. Herschel's discovery of Uranus also demonstrates how technological innovation drives astronomical progress. His telescopes, built in his own workshop using techniques he develops himself, achieve unprecedented resolution and light-gathering power. The patient craftsmanship required to grind large mirrors and construct stable telescope mounts becomes as important to astronomical discovery as mathematical theory or observational skill. The systematic survey of the night sky made possible by improved telescopes reveals a universe far richer and more complex than previous generations had imagined. Herschel discovers not just new planets, but double stars, pairs of stars orbiting around their common center of mass under gravitational attraction. These stellar systems provide direct observational confirmation that Newton's law of gravitation operates throughout the universe, not just within the solar system. The study of double stars also opens entirely new avenues for astronomical investigation. By observing the orbital motions of binary star systems, astronomers can determine stellar masses and distances using the same gravitational principles that govern planetary motion. This work establishes the foundation for stellar astronomy, transforming distant points of light into measurable physical objects with known properties. Newton's gravitational theory also enables the first successful measurements of stellar parallax, the tiny apparent shifts in star positions caused by Earth's orbital motion around the Sun. These measurements, finally achieved in the 1830s using telescopes and techniques undreamed of in Newton's time, provide direct observational proof of Earth's motion, while revealing the enormous distances to even the nearest stars. The parallax measurements transform humanity's understanding of cosmic scale. The nearest stars prove to be so distant that light takes years to travel from them to Earth, introducing the concept of light years as a unit of cosmic distance. The universe revealed by parallax measurements is vastly larger than even post-Copernican astronomy had suggested, filled with suns scattered across distances that dwarf the entire solar system. These discoveries of cosmic scale prepare the ground for even more revolutionary insights about the nature of stars and galaxies. If stars are distant suns, some might be intrinsically brighter or fainter than our Sun. Some might be larger or smaller. Some might be hotter or cooler. The diversity of stellar properties becomes a new frontier for astronomical investigation, requiring new instruments and techniques to analyze the light from distant stars. The development of increasingly sophisticated mathematical techniques for analyzing gravitational systems also leads to insights about the stability and evolution of planetary systems. Newton's equations reveal that while two-body systems like the Earth-Sun pair are perfectly stable, systems with three or more gravitating bodies can exhibit complex, sometimes chaotic behavior. This mathematical complexity hints at dynamical richness in cosmic systems that will require centuries to fully understand. The success of Newtonian mechanics in explaining celestial phenomena also stimulates investigations of Earth's own gravitational field. Careful measurements of gravitational acceleration at different locations reveal that Earth is not a perfect sphere, but slightly flattened at the poles, a deformation caused by the planet's rotation. These geodetic surveys provide some of the most precise tests of gravitational theory, while advancing our understanding of Earth's shape and internal structure. The mathematical tools developed for celestial mechanics find applications throughout physics and engineering. The calculus created to analyze planetary motion becomes essential for understanding any system involving continuous change. The principle of conservation of energy, first clearly formulated in the context of gravitational systems, emerges as a fundamental law governing all physical processes. As the 18th century progresses, the success of Newtonian mechanics inspires confidence that the entire universe operates according to discoverable mathematical laws. This mechanical worldview, often called the clockwork universe, suggests that if the position and velocity of every particle could be known at any moment, the entire future history of the cosmos could in principle be calculated. While this deterministic vision will eventually be modified by quantum mechanics and chaos theory, it provides the conceptual framework for 2 centuries of scientific progress. The practical applications of gravitational theory extend beyond pure astronomy to navigation, cartography, and timekeeping. Accurate predictions of celestial motions enable improvements in maritime navigation that facilitate global exploration and commerce. The regularity of astronomical phenomena provides standards for measuring time that surpass any mechanical clock. The mapping of gravitational variations across Earth's surface aids in understanding geological structure and mineral distribution. Newton's synthesis of terrestrial and celestial physics also has profound philosophical implications. The demonstration that the same mathematical laws govern motion throughout the universe suggests a fundamental unity underlying natural phenomena. This insight encourages the search for universal principles in other areas of physics and establishes mathematics as the language in which the laws of nature are written. The influence of Newtonian mechanics extends well beyond the physical sciences to shape Enlightenment thinking about society, politics, and human nature. If the cosmos operates according to rational mathematical principles, perhaps human societies could be organized according to similarly rational principles. The scientific method pioneered in astronomy becomes a model for investigating everything from economics to psychology. Yet even as Newtonian mechanics achieves unprecedented success in explaining celestial phenomena, new observations begin to reveal limitations and puzzles that will eventually require new theoretical frameworks. Small discrepancies in planetary motions, subtle effects in the orbits of comets, and anomalies in the behavior of light all hint at deeper layers of physical reality that Newton's theory cannot fully explain. These observational puzzles don't diminish Newton's achievement, but rather point toward the ongoing nature of scientific progress. Each successful theory reveals new phenomena and raises new questions that drive further investigation. The mechanical universe revealed by Newton's mathematics becomes the foundation for even more sophisticated understanding of cosmic structure and evolution. As the age of gravitational astronomy reaches maturity in the early 19th century, new technologies and observational techniques are beginning to transform humanity's ability to study the cosmos. Improved telescopes reveal details of planetary surfaces and stellar systems that Newton could never have imagined. New forms of analysis, particularly the emerging science of spectroscopy, promise to reveal the physical composition and properties of distant stars and nebulae. The systematic survey of the heavens made possible by Newtonian theory and improved instruments is about to reveal that our solar system, vast as it now appears, is merely a tiny part of a much grander cosmic structure filled with star systems, clusters, and mysterious nebulous objects whose nature and distance remain to be determined. In the rolling hills of West Sussex, England, stands a monument to human ingenuity and cosmic curiosity, the ruins of what was once the largest telescope in the world. Built by William Herschel in the 1780s, this 40-foot reflecting telescope represented humanity's most ambitious attempt yet to peer deeper into the cosmos than ever before. Though the great instrument has long since fallen into decay, its legacy marks the beginning of an era when telescope makers and astronomers joined forces to push the boundaries of the observable universe ever outward. The 19th century dawns with astronomy poised for revolutionary discoveries. Newton's gravitational theory has provided the mathematical framework for understanding celestial motions, while improvements in telescope design and construction promise to reveal cosmic details invisible to earlier generations. But perhaps most importantly, a new tool is about to transform astronomy from a science limited to measuring positions and motions into one capable of determining the physical nature of distant stars and nebulae. This revolutionary tool is spectroscopy, the analysis of light broken down into its component colors by prisms or diffraction gratings. When astronomers first begin passing starlight through prisms in the early 1800s, they discover something unexpected. The continuous rainbow of colors is crossed by dark lines at specific wavelengths. These absorption lines, as they come to be known, provide a kind of fingerprint that reveals the chemical composition of distant stars. The development of stellar spectroscopy begins almost by accident when German optician Joseph von Fraunhofer notices dark lines in the spectrum of sunlight while testing telescope optics. His careful mapping of these lines creates the first detailed atlas of the solar spectrum, cataloguing hundreds of dark absorption features without understanding their significance. But within decades, laboratory experiments reveal that each chemical element produces its own unique pattern of spectral lines, allowing astronomers to determine stellar composition by comparing stellar spectra with laboratory standards. This discovery transforms our understanding of the cosmos. For the first time in human history, astronomers can determine not just where celestial objects are and how they move, but what they're made of. The same iron, hydrogen, and calcium found on Earth prove to exist in distant stars, establishing a fundamental unity of matter throughout the universe. Spectroscopy also reveals that stars have different temperatures and compositions. Some stars show strong hydrogen lines, others display complex patterns indicating the presence of metals. This diversity suggests that stars, far from being identical points of light, are individual worlds with their own physical characteristics and evolutionary histories. The combination of improved telescopes and spectroscopic analysis enables astronomers to begin systematic surveys of stellar properties. Caroline Herschel, sister of William and an accomplished astronomer in her own right, discovers multiple comets and catalogues nebulous objects that will later prove crucial for understanding galactic structure. Her work exemplifies the expanding role of women in astronomy, as improved instruments make observational astronomy accessible to dedicated observers, regardless of formal training. The search for new planets continues to drive telescope development and observational technique. When careful analysis of Uranus's orbit reveals small deviations from predictions based on gravitational attraction from known planets, mathematicians Urbain Le Verrier and John Couch Adams independently calculate where an undiscovered planet must be located to account for these perturbations. The subsequent telescopic discovery of Neptune in 1846 found almost exactly where theory predicts, provides stunning confirmation of Newtonian mechanics, while demonstrating astronomy's power to discover invisible worlds through mathematical analysis. The Neptune discovery represents a triumph of theoretical astronomy. Never before has a major celestial object been discovered through calculation rather than observation. The success of this mathematical approach encourages astronomers to look for other gravitational influences that might reveal additional hidden worlds, leading to systematic searches that will eventually uncover Pluto and the outer reaches of the solar system. Between Mars and Jupiter, Telescopic surveys reveal an entirely unexpected population of small worlds. The discovery of Ceres in 1801, followed by Pallas, Juno and Vesta, initially leads astronomers to classify these objects as planets. But as more similar objects are found, it becomes clear that a new category of celestial body exists: the asteroids, or minor planets. This asteroid belt represents the scattered remnants of a planet that never formed, providing insights into the early history of the solar system. The study of asteroids also reveals the dynamic complexity of the solar system. Some asteroids follow highly elliptical orbits that cross planetary paths. Others cluster in stable regions governed by gravitational resonances with Jupiter. This orbital complexity demonstrates that the solar system is not a simple collection of planets following isolated paths, but a gravitationally interacting system where the motion of each body influences all others. Meanwhile, telescopic observations of the planets themselves reveal worlds of unexpected diversity and complexity. Mars shows seasonal changes in surface markings that suggest vegetation and possibly even intelligent life. Jupiter displays a complex system of coloured bands, and the famous Great Red Spot, a storm larger than Earth that has persisted for centuries. Saturn's ring system resolves into multiple distinct rings separated by gaps, creating a structure of elegant complexity that challenges theories of ring formation and stability. These planetary observations raise profound questions about the nature and origin of worlds. If Mars shows seasonal changes, might it harbour life? If Jupiter generates its own heat and possesses a complex atmospheric system? What does this reveal about planetary formation? If Saturn's rings are composed of countless small particles, what forces maintain their intricate structure over geological time? The application of spectroscopy to planetary observation begins to answer some of these questions while raising new ones. The Martian atmosphere proves to contain water vapour, strengthening the possibility of life on the red planet. Jupiter's spectrum reveals clouds composed of ammonia and methane, suggesting an atmosphere utterly alien to terrestrial experience. These discoveries establish comparative planetology as a new branch of astronomy, encouraging systematic study of how different worlds form and evolve. Telescope technology itself undergoes revolutionary improvement during this period. The development of achromatic lenses eliminates the colour distortions that plagued earlier refracting telescopes, while advances in mirror making enable the construction of reflecting telescopes far larger than anything previously possible. The Earl of Ross's 6-foot reflecting telescope, completed in Ireland in 1845, achieves resolution sufficient to reveal spiral structure in nebulous objects that had previously appeared as mere fuzzy patches. Ross's observations of spiral nebulae proved particularly significant for understanding cosmic structure. His detailed drawings show that many nebulous objects have elegant spiral arms extending from central hubs, suggesting organized structure rather than random clouds of luminous matter. The nature and distance of these spiral forms remain mysterious, but their obvious structure implies that they are significant cosmic phenomena deserving systematic study. Photography begins to revolutionize astronomical observation during the latter half of the 19th century. Photographic plates can accumulate light over long exposures, revealing faint details invisible to the human eye even through large telescopes. More importantly, photographs provide permanent records that can be measured and analyzed long after the observation, enabling precision impossible with visual observation alone. The marriage of photography and spectroscopy creates astrophotography, allowing astronomers to record spectra of stars too faint for visual analysis. This combination reveals that the universe contains stars far more diverse than naked eye observation had suggested. Some stars prove to be intrinsically much brighter than the Sun, others much fainter. Some show unusual spectral features indicating exotic compositions or physical conditions unknown in terrestrial experience. The systematic photographing of star fields also leads to serendipitous discoveries. Stars that appear constant to visual observation sometimes show variability when monitored photographically over months or years. Some variables change brightness in regular cycles, others fluctuate irregularly. These variable stars provide the first evidence that stellar properties can change over time, suggesting that stars have life cycles involving birth, evolution, and death. Perhaps most significantly, photographic surveys begin to reveal the true scale and structure of our cosmic neighborhood. The Milky Way, that faint band of light visible on dark nights, resolves into countless individual stars when photographed through large telescopes. This photographic confirmation of Galileo's telescopic observation establishes that our solar system lies within a vast stellar system containing billions of individual suns. But even more mysterious are the nebulous objects scattered throughout the sky. Some nebulae resolve into star clusters when observed through powerful telescopes, but others maintain their fuzzy appearance even under the highest magnification. William Herschel had catalogued many of these objects, and his son John extends this work by systematically surveying nebulae in both northern and southern hemispheres. Their combined catalogues list thousands of nebulous objects whose nature remains unclear. The spectroscopic analysis of nebulae reveals two distinct types. Some show the continuous spectra characteristic of stellar collections, confirming that they are distant star clusters, but others display bright emission lines indicating glowing gas heated by nearby stars. These gaseous nebulae provide the first direct evidence for diffuse matter in interstellar space, showing that the cosmos contains not just stars and planets, but vast clouds of luminous gas. The study of nebula spectra also reveals new chemical elements. Certain emission lines in nebula spectra don't match any known terrestrial element, leading to the hypothesis that space contains elements unknown on Earth. The discovery of helium in the solar spectrum before its identification on Earth demonstrates that astronomical spectroscopy can reveal the existence of new elements, expanding our understanding of matter itself. As astronomical catalogues grow and observational techniques improve, patterns begin to emerge that hint at larger cosmic organization. Variable stars cluster in certain regions of the sky, nebulae show preferred orientations, and stellar densities vary dramatically across different parts of the heavens. These patterns suggest that our stellar neighborhood has structure and organization extending far beyond the simple collection of randomly distributed stars that earlier astronomers had imagined. The measurement of stellar distances using parallax, finally achieved in the 1830s, provides the first reliable scale for measuring cosmic dimensions. The nearest stars prove to be so distant that their light takes years to reach Earth, establishing the light year as a natural unit for cosmic measurement. But even more significantly, these distance measurements reveal that stars vary enormously in intrinsic brightness, with some stars thousands of times more luminous than the Sun, while others emit only a tiny fraction of solar energy. This diversity of stellar properties suggests that stars, like planets, come in many different types with various physical characteristics. The classification of stellar spectra into different types, initially designated by letters of the alphabet, creates the first systematic framework for understanding stellar diversity. This classification reveals that stellar properties correlate in systematic ways, with color, temperature, and spectral features all related through underlying physical principles. The discovery of binary star systems, where two stars orbit around their common centre of mass, provides the first opportunity to measure stellar masses directly. By observing the orbital motions of binary pairs and applying Newtonian mechanics, astronomers can determine the masses of individual stars. These measurements reveal that stellar masses, like stellar luminosities, vary over a wide range, with some stars containing dozens of times more matter than the Sun, while others are much less massive. The systematic study of stellar properties, masses, luminosities, temperatures, and compositions begins to reveal relationships that hint at underlying physical processes governing stellar behavior. Stars with certain masses tend to have specific luminosities and temperatures, suggesting that stellar properties are not random, but follow natural laws governing how matter behaves under extreme conditions of temperature and pressure. As the 19th century draws to a close, astronomy stands poised for even greater revelations. The combination of large telescopes, photographic techniques, and spectroscopic analysis has revealed a universe far more complex and diverse than previous generations could have imagined. Stars prove to be suns with their own individual characteristics and evolutionary histories. Nebulae reveal the existence of glowing gas clouds and distant stellar systems. The solar system expands to include minor planets and outer worlds, whose very existence demonstrates the power of mathematical astronomy. Yet many of the most fundamental questions about cosmic structure remain unanswered. What is the true nature and distance of spiral nebulae? How large is the Milky Way system, and what lies beyond it? Do stars form from nebular matter? And if so, how do they evolve over time? What forces power stellar luminosity? And why do different stars have such different properties? These questions will soon find their answers through even more powerful telescopes and sophisticated analysis techniques. The 20th century is about to dawn with revolutionary discoveries that will reveal not just the structure of our own galactic system, but the existence of countless other galaxies scattered throughout a universe whose size and age exceed the boldest 19th century speculations. In the decades that followed those revolutionary 19th century discoveries, astronomy continued its relentless march toward understanding the true scale and nature of the cosmos. The early 20th century brought revelations that transformed our picture of the universe from a single galaxy of stars to an infinite expanse filled with billions of galaxies, each containing billions of stars. Edwin Hubble's observations at Mount Wilson revealed that those mysterious spiral nebulae were actually distant galaxies, and his subsequent discovery that the universe itself is expanding forever changed our understanding of cosmic history and destiny. The mid-20th century ushered in the space age, lifting astronomy beyond the filtering veil of Earth's atmosphere for the first time in human history. The Hubble Space Telescope, launched in 1990, became humanity's most productive eye on the universe, revealing cosmic phenomena from nearby planetary systems to the most distant galaxies visible in the observable universe. For over 3 decades, Hubble's images have shaped our understanding of stellar evolution, galactic structure, dark matter, and the accelerating expansion of the cosmos. But as remarkable as Hubble's achievements have been, the telescope was designed using 1980s technology and has always been limited by the size of its primary mirror, just 2.4 meters across. As the 21st century progressed, astronomers dreamed of a successor that could see deeper into space and further back in time, revealing the universe's earliest epochs when the first stars and galaxies were forming. That dream became reality on Christmas Day 2021, when the James Webb Space Telescope began its million-mile journey to a gravitationally stable point beyond the Moon's orbit. Named for the NASA administrator who shepherded the Apollo program, Webb represents the most ambitious and complex astronomical instrument ever built, designed to observe the cosmos in infrared light, with unprecedented sensitivity and resolution. Webb's design reflects lessons learned from decades of space-based astronomy. Where Hubble observes primarily invisible light, Webb is optimized for infrared observation, allowing it to peer through cosmic dust clouds that obscure visible light and to detect the stretched, red-shifted light from the most distant galaxies. Its primary mirror, composed of 18 hexagonal segments that unfold like a golden flower in space, spans 6.5 meters, nearly 3 times Hubble's diameter and 6 times its light-gathering area. The engineering challenges overcome in Webb's construction represent marvels of 21st century technology. The telescope must operate at temperatures just 40 degrees above absolute zero to prevent its own heat from overwhelming the faint infrared signals it seeks to detect. A tennis court-sized sun shield composed of 5 ultra-thin layers protects the instruments from solar radiation while allowing the telescope to peer into the depths of space. Webb's journey to its operational position demonstrates the continuing marriage of astronomical ambition with orbital mechanics pioneered in Newton's era. The telescope travels to the second Lagrange point, a location where Earth's and the Sun's gravity balance to create a stable observing platform. This gravitational sweet spot, located 1.5 million kilometers from Earth, allows Webb to maintain its position relative to our planet while keeping its sun shield constantly oriented toward the Sun. The telescope's first images, released in July 2022, immediately revealed capabilities that exceeded even optimistic expectations. Webb's deep-field observations captured galaxies so distant that their light began its journey when the universe was less than 5% of its current age. These ancient galaxies appear as they existed just a few 100 million years after the Big Bang, during the cosmic epoch when the first generation of stars was beginning to illuminate the primordial darkness. Perhaps most remarkably, Webb's observations reveal that large mature galaxies existed much earlier in cosmic history than theoretical models had predicted. These early galaxies are not the small, primitive structures that astronomers expected from the universe's youth, but rather massive, organized systems that must have formed surprisingly quickly after the Big Bang. This discovery is forcing astronomers to reconsider theories of galaxy formation and the early evolution of cosmic structure. Webb's infrared vision also excels at studying stellar nurseries, the dense clouds of gas and dust where new stars are born. These stellar cradles, opaque to visible light, become transparent to Webb's infrared instruments, revealing the process of star formation in unprecedented detail. The telescope's observations show how gravity sculpts collapsing gas clouds into the dense cores that eventually ignite nuclear fusion and become stars. The study of exoplanets, worlds orbiting other stars, represents another area where Webb is revolutionizing astronomical knowledge. The telescope's sensitive spectrometers can analyze the atmospheres of distant planets by observing how starlight changes as planets pass in front of their host stars. These transit observations reveal the chemical composition of alien atmospheres, providing clues about planetary formation, evolution, and potentially even the presence of life. Webb's first exoplanet atmospheric analyses have already detected water vapor, carbon dioxide, and other molecules in the atmospheres of distant worlds. Some of these planets orbit in their star's habitable zone, the region where liquid water could exist on planetary surfaces. While Webb cannot directly detect life on these distant worlds, its atmospheric studies are laying the groundwork for future missions that might identify biosignatures in exoplanet atmospheres. The telescope's observations of our own solar system provide new perspectives on familiar worlds. Webb's infrared capabilities reveal thermal patterns on planetary surfaces, atmospheric circulation systems, and the composition of comets and asteroids with unprecedented clarity. Even well-studied objects like Jupiter reveal new phenomena when observed through Webb's advanced instruments. Webb's discoveries extend beyond individual objects to cosmic phenomena that shape the universe's large-scale structure. The telescope's observations of distant supernovae, stellar explosions that briefly outshine entire galaxies, provide insights into cosmic acceleration and the mysterious dark energy that appears to be driving the universe's expansion at an ever-increasing rate. The detection and study of gravitational waves, first achieved by ground-based detectors in 2015, opens an entirely new window on cosmic phenomena. These ripples in space-time itself, predicted by Einstein's general relativity, carry information about some of the universe's most extreme events: colliding black holes, merging neutron stars, and possibly even echoes from the Big Bang itself. Webb's coordination with gravitational wave detectors exemplifies modern astronomy's multi-messenger approach to studying cosmic phenomena. When gravitational wave detectors sense the space-time ripples from a cosmic collision, Webb and other telescopes immediately search for electromagnetic counterparts, the light produced by these violent events. This coordinated approach provides a more complete picture of cosmic phenomena than any single type of observation could achieve. The study of dark matter and dark energy, which together comprise about 95% of the universe's content, represents one of contemporary astronomy's greatest challenges. While these mysterious components cannot be observed directly, their gravitational effects shape the formation and evolution of cosmic structure. Webb's observations of galaxy formation and cosmic evolution provide crucial data for understanding how dark matter and dark energy influence the universe's development. Webb's deep field observations also contribute to the ongoing effort to measure the universe's expansion rate, a project that began with Hubble's discovery of cosmic expansion nearly a century ago. Precise measurements of this expansion rate, known as the Hubble constant, reveal tensions between different measurement methods that may indicate new physics beyond our current understanding of cosmic evolution. The technological innovations developed for Webb are already inspiring the design of even more ambitious space telescopes. Proposed projects include interferometric arrays of space-based telescopes that could directly image Earth-like exoplanets, extremely large space telescopes with mirrors hundreds of times Webb's size, and specialized instruments designed to search for specific signatures of life in exoplanet atmospheres. Ground-based astronomy continues to advance alongside space-based observations. The new generation of extremely large telescopes with mirrors 30 meters or more in diameter will achieve resolution surpassing even space-based instruments for certain types of observations. Adaptive optics systems that correct for atmospheric turbulence in real time allow ground-based telescopes to achieve theoretical resolution limits, rivaling space-based performance for many applications. The emerging field of computational astronomy uses artificial intelligence and machine learning to analyze the vast data sets produced by modern telescopes. These computational tools can identify patterns in astronomical data that would be impossible for human astronomers to detect, discovering new types of astronomical objects and revealing subtle correlations in cosmic phenomena. Citizen science projects allow amateur astronomers and interested members of the public to contribute to astronomical research by analyzing telescope data, classifying galaxy types, or searching for unusual objects. These crowdsourced research projects have led to significant discoveries while engaging the public in the process of astronomical exploration. The international nature of modern astronomy reflects the global scale of contemporary scientific collaboration. Webb itself is a joint project of NASA, the European Space Agency, and the Canadian Space Agency, with contributions from astronomers worldwide. This international cooperation enables projects too ambitious for any single nation, while fostering the sharing of knowledge and resources that accelerate scientific progress. Future astronomical missions will push even further into the unknown. Proposed gravitational wave detectors in space could observe cosmic collisions throughout the universe, with sensitivity impossible from Earth-based instruments. Advanced propulsion systems might enable interstellar probes that could directly explore nearby star systems, providing ground truth for astronomical observations of exoplanets. The search for extraterrestrial life, long relegated to the realm of speculation, has become a legitimate astronomical research program. Webb's atmospheric studies of exoplanets, combined with increasingly sophisticated theoretical understanding of how life might arise and evolve, are bringing us closer to answering one of humanity's most profound questions. Are we alone in the universe? The philosophical implications of modern astronomical discoveries extend far beyond technical scientific questions. The realization that Earth orbits an ordinary star in a typical galaxy among billions of similar galaxies has fundamentally changed humanity's perspective on our place in the cosmos. Yet paradoxically, the more we learn about the precise conditions required for life to emerge and thrive, the more remarkable our existence appears. Webb's observations of the early universe provide insights into cosmic origins that complement our understanding of terrestrial history. The elements that comprise our bodies, carbon, oxygen, nitrogen, and others, were forged in the cores of ancient stars that lived and died billions of years ago. We are, quite literally, made of star stuff, connected to the cosmos through the nuclear processes that created the chemical elements essential for life. The rapid pace of astronomical discovery in the Webb era demonstrates that our understanding of the universe continues to evolve. Each new observation has the potential to reveal unexpected phenomena that challenge existing theories and open new avenues for investigation. The history of astronomy shows that the universe consistently proves more complex, more beautiful, and more surprising than our theoretical models predict. As Webb continues its mission and future telescopes prepare for launch, astronomy stands poised for discoveries that may fundamentally transform our understanding of cosmic history, structure, and evolution. The questions that drive contemporary astronomical research. How did the first stars and galaxies form? How common is life in the universe? What are dark matter and dark energy? May find their answers in the coming decades. The tools and techniques being developed for studying the cosmos also have applications closer to home. Advancing technologies in computing, materials science, and engineering that benefit society in countless ways. The same innovations that enable Webb to peer into the depths of space drive, advances in medical imaging, communications technology, and environmental monitoring. The Webb era represents more than just technological achievement. It embodies humanity's enduring commitment to understanding our place in the cosmos. The same curiosity that led our ancestors to track the movements of stars and planets now drives us to peer back toward the very beginning of time itself, seeking to understand how the universe evolved from its earliest moments to the rich, complex cosmos we observe today. As we continue this grand journey of discovery, we carry forward the legacy of every astronomer who has ever looked up at the night sky and wondered what secrets it might hold. As we near the end of our gentle journey through the history of astronomy, it's worth pausing to reflect on the extraordinary path we've travelled together. We began our story around ancient campfires, with our earliest ancestors tilting their heads back to gaze at a star-filled sky unmarked by the glow of cities or the trails of aircraft. We end it in an era when humanity peers back toward the very beginning of time itself, using instruments of incredible sophistication to study galaxies so distant that their light began its journey when the universe was still in its cosmic infancy. What connects these two moments, separated by tens of thousands of years and unimaginable advances in knowledge and technology, is something beautifully constant about human nature. Our irrepressible curiosity about the cosmos that surrounds us. The same fundamental questions that occurred to those first stargazers still drive astronomical research today. What are those lights in the sky? How do they move? What is our place in the larger scheme of things? How did it all begin, and where is it all heading? The answers we have discovered along the way have consistently revealed a universe far grander, stranger, and more beautiful than anyone could have imagined. Each generation of astronomers has pushed the boundaries of the known cosmos outward, only to discover that new mysteries await at every scale of investigation. Those patient Babylonian astronomers, recording planetary positions on clay tablets night after night, developed mathematical techniques so sophisticated that they could predict eclipses decades into the future. Their work demonstrated for the first time that the seemingly chaotic movements of celestial bodies follow precise mathematical laws, a discovery that laid the foundation for all of science. The Greek astronomers who inherited and built upon Babylonian knowledge brought something new to cosmic investigation: the conviction that human reason could uncover the physical principles underlying celestial phenomena. When Aristarchus proposed that Earth orbits the Sun, he wasn't just offering a new calculating method. He was suggesting that mathematical reasoning could reveal truths about the actual structure of the universe. Islamic astronomers preserved and extended this classical heritage while developing new standards of observational precision and mathematical sophistication. Working in observatories from Baghdad to Cordoba, they refined planetary theory, improved astronomical instruments, and established institutional frameworks for collaborative research that provided models for all later scientific investigation. The Renaissance astronomers who revived and transformed European astronomy built directly upon this Islamic foundation. Copernicus, drawing upon centuries of accumulated observations and theoretical development, had the courage to propose that Earth is simply another planet orbiting the Sun. Tycho Brahe achieved observational precision that wouldn't be surpassed for centuries, while Kepler discovered that planets follow elliptical orbits governed by mathematical laws of exquisite simplicity and beauty. Galileo's telescope opened an entirely new era in astronomical discovery. His observations of lunar mountains, Jupiter's moons, and the phases of Venus provided the first direct visual evidence for the heliocentric system, while establishing observational astronomy as an experimental science. The universe revealed by Galileo's simple telescope was no longer the small, Earth-centered cosmos of ancient tradition, but a vast realm of worlds in motion. Newton's mathematical synthesis of terrestrial and celestial physics demonstrated that the same laws govern motion throughout the universe. His theory of universal gravitation explained everything from falling apples to planetary orbits through a single mathematical principle, establishing the scientific method as humanity's most powerful tool for understanding the natural world. The great telescopes of the 18th and 19th centuries revealed cosmic diversity that earlier astronomers had never suspected. Spectroscopy showed that distant stars are composed of the same elements found on Earth, while binary star observations confirmed that Newton's laws operate throughout the cosmos. The discovery of Uranus and Neptune demonstrated astronomy's predictive power, while the asteroid belt revealed unexpected complexity in the solar system's structure. Photography revolutionized astronomical observation, allowing the accumulation of light over long exposures and providing permanent records for detailed analysis. Variable stars revealed that stellar properties change over time, while parallax measurements finally proved Earth's orbital motion while establishing the enormous scale of interstellar distances. The 20th century brought revelations that transformed our understanding of cosmic structure and evolution. Hubble's observations showed that spiral nebulae are distant galaxies, each containing billions of stars, and that the universe itself is expanding from an initial state of incredible density and temperature. The discovery of cosmic background radiation provided direct evidence for the Big Bang, while gravitational wave detectors opened entirely new windows on cosmic phenomena. The space age lifted astronomy beyond Earth's atmospheric veil for the first time in human history. The Hubble Space Telescope revealed cosmic phenomena from nearby planetary systems to the most distant observable galaxies, while space-based observatories studying different wavelengths of light provided comprehensive views of cosmic structure and evolution. Now, in the James Webb era, we are witnessing discoveries that challenge our understanding of galaxy formation, stellar evolution, and planetary system development. Webb's infrared vision reveals star formation in unprecedented detail, while studying the atmospheres of distant exoplanets and peering back toward the universe's earliest epochs. Yet for all our technological sophistication and accumulated knowledge, the fundamental experience of astronomical wonder remains unchanged. When we look up at a dark sky filled with stars, whether through the eyepiece of a great telescope or simply with our own eyes, we are participating in the same act of curiosity and awe that has defined our species since its earliest days. This continuity of wonder across millennia speaks to something profound about astronomy's place in human culture. Unlike many other sciences which require specialized training to appreciate fully, astronomy remains accessible to anyone willing to look up at the night sky with an open sense of curiosity. The stars that inspired the first astronomical questions still shine down on us today, still inviting us to wonder about our place in the cosmos. The democratization of astronomical knowledge through improved instruments and educational resources means that more people than ever before can participate in the ongoing process of cosmic discovery. Amateur astronomers make important contributions to professional research, while citizen science projects allow interested individuals to analyze telescope data and contribute to our understanding of the universe. The international character of modern astronomy reflects the universal nature of cosmic curiosity. Astronomers from every continent collaborate on projects too ambitious for any single nation, sharing telescopes, data, and discoveries in a global enterprise that transcends political and cultural boundaries. The James Webb Space Telescope itself exemplifies this international cooperation, representing contributions from multiple space agencies and thousands of individuals working together toward common goals. The technological innovations driven by astronomical research continue to benefit society in countless ways beyond pure scientific discovery. The same technologies that enable space telescopes to peer into the depths of the cosmos, advance medical imaging, communication systems, and environmental monitoring. The computational techniques developed for analyzing astronomical data contribute to artificial intelligence and machine learning research with applications throughout modern society. But perhaps most importantly, astronomy continues to provide perspective on humanity's place in the cosmos that shapes how we think about ourselves and our responsibilities. The realization that Earth is a small planet orbiting an ordinary star in a typical galaxy among billions of others fundamentally alters our perspective on terrestrial concerns and cosmic significance. Yet paradoxically, the more we learn about the precise conditions required for life to emerge and thrive, the more remarkable our existence appears. The elements that compose our bodies were forged in the cores of ancient stars. The stable climate that allowed complex life to evolve depends on countless cosmic factors, ranging from our position in the galaxy to the composition of our atmosphere. We are intimately connected to the cosmos through the nuclear processes that created the chemical elements essential for life. The search for life beyond Earth, once relegated to the realm of speculation, has become a legitimate scientific enterprise. Webb's atmospheric studies of exoplanets, combined with increasingly sophisticated understanding of how life might arise and evolve, are bringing us closer to answering one of humanity's most profound questions. Are we alone in the universe? The rapid pace of astronomical discovery demonstrates that our understanding of the cosmos continues to evolve at an accelerating rate. Each new observation has the potential to reveal unexpected phenomena that challenge existing theories and open new avenues for investigation. The history of astronomy shows that the universe consistently proves more complex, more beautiful, and more surprising than our theoretical models predict. The questions that drive contemporary astronomical research represent natural extensions of the same curiosity that motivated our ancestors. How did the first stars and galaxies form? What are dark matter and dark energy? How common is life in the universe? What lies beyond the observable horizon of our expanding cosmos? These questions may find their answers in the coming decades, though history suggests that each answer will reveal new mysteries waiting to be explored. Future astronomical instruments promise discoveries that will transform our understanding of cosmic history and structure. Extremely large ground-based telescopes will achieve unprecedented resolution, while space-based observatories will study the universe across the entire electromagnetic spectrum with sensitivity impossible from Earth's surface. Gravitational wave detectors will observe cosmic collisions throughout the universe, while proposed interstellar probes might provide direct exploration of nearby star systems. The emergence of computational astronomy and artificial intelligence in astronomical research opens new possibilities for discovering patterns in cosmic phenomena that would be impossible for human astronomers to detect. These tools may reveal relationships and correlations in astronomical data that lead to entirely new understanding of how the universe operates. As we stand on the threshold of these future discoveries, we carry forward the legacy of every astronomer who has ever contributed to our understanding of the cosmos. From the anonymous observer who first noticed that certain stars move in patterns to the teams of scientists operating the most sophisticated space telescopes, each generation has added to the accumulated treasury of cosmic knowledge. This progression from wonder to understanding represents one of humanity's greatest intellectual achievements. We have transformed our relationship with the cosmos from fearful superstition to confident investigation, from passive observation to active exploration. Yet the fundamental human experience of astronomical wonder remains unchanged, connecting us across cultures and centuries in shared appreciation for the beauty and mystery of the universe. The story of astronomy is ultimately the story of human curiosity itself, our refusal to accept that the mysteries of existence are beyond understanding, our commitment to careful observation and logical reasoning, our willingness to revise our most cherished beliefs when confronted with new evidence. These qualities, exemplified in astronomical research, represent the best aspects of human nature and our highest aspirations as thinking beings. Tonight, when you look up at the stars, you're participating in an unbroken chain of curiosity that stretches back to the very beginning of human consciousness. The same cosmic forces that shape the evolution of galaxies and stars also guided the formation of our solar system and the emergence of life on Earth. We are not separate from the universe we study. We are part of it, products of cosmic evolution who have developed the remarkable ability to understand our own origins. The questions that began around ancient campfires continue to drive our most sophisticated research programs. The wonder that inspired the first astronomical observations still motivates the construction of great telescopes and the launching of space missions. The desire to understand our place in the cosmos remains as powerful today as it was when our ancestors first looked up at the night sky and wondered what they were seeing. This continuity of curiosity across millennia suggests that the astronomical quest will continue as long as human consciousness exists. Each new discovery opens doors to further questions. Each answer reveals new mysteries waiting to be explored. The universe appears to be not just stranger than we imagine, but stranger than we can imagine, a cosmic puzzle of infinite depth and beauty that will reward investigation for as long as humanity retains its sense of wonder. As you drift towards sleep tonight, perhaps you'll carry with you this sense of connection to the cosmic story we've explored together. The same atoms that formed in ancient stellar cores now comprise your body and brain. The same physical laws that govern the motions of galaxies also guide the biochemical processes that sustain your life. The same curiosity that drove our ancestors to map the movements of stars now enables us to peer back toward the very beginning of time itself. You are, quite literally, the universe becoming aware of itself, a temporary arrangement of star stuff that has achieved the remarkable ability to contemplate its own origins and destiny. In your questions about the cosmos, you participate in the ongoing human effort to understand existence itself. In your wonder at the night sky, you connect with every human who has ever looked up and marveled at the beauty and mystery of the stars. The gentle arc of curiosity that began around the first campfires continues its journey through you and through everyone who still feels that sense of awe when confronted with the infinite depths of space and time. The stars that called to our earliest ancestors continue to call to us, inviting us to join the eternal human quest to understand our place in the magnificent, mysterious, ever-surprising cosmos we call home. Sweet dreams, fellow travelers through space and time. May your rest be peaceful, your wonder undimmed, and your curiosity about the cosmos continue to connect you to the greatest adventure in human history, our ongoing journey to understand the universe and our place within it. Clear skies and boundless wonder, the Sleepy Astronomer.